Okay, so good morning, everyone. Welcome to day 2 of the Joint Senate Workshop. My name is Lydia Cucurull. I work for NOAA OER, and I will be chairing the session. I've been told to remind you to stay for a couple minutes at the break time. We're going to have a group picture, so don't go anywhere after the 3 sessions. So today we're going to start with the marine applications, and the first talk is by Guillaume Vernieres, and the title is Implementation of JEDI-SOCA in EMC's weakly coupled JEDIs.
Thank you. So it's a large group of people that obviously collaborated to make things happen. I decided to not list people because I would have forgotten somebody. So instead of getting in trouble with 1 or 2 persons, I'll get in trouble with everybody. If you have questions, just do send me an email and I will be able to direct you to the experts. Okay, so that's the structure of my talk, which hopefully will make sense. I'll give you a brief overview of what the Global Forecast System version 17 is going to be, how we're going to be implementing the weakly coupled DA system for the JFSB 17. That's going to involve some global workflow talk, and our tentative plan for the implementation of JEDI-SOCA. And then I'll finish with a system optimization, as in how are we going to make sure that we are constantly improving our implementation. And I'll show some preliminary results. So JFSB 17, we are going to be using the coupled UFS, and by coupled we mean we will have MV3 for the atmosphere, WaveWatch 3 for waves, GOCART, size 6, which is our sea ice model, MOM6 for the ocean, NOAA MP for the land surface model. And we have, inside of the physics of MV3, we have something that's called NSST and provides boundary condition to the atmosphere and is used also to compute fluxes. And one of the big difference is that NSST now is going to be getting the foundation temperature from the ocean, which is going to be interesting. All right, so in terms of DA, for MV3, for the atmosphere in general, there is going to be changes obviously to GSI, but we are going to be using GSI, so some upgraded version of V16.3 or wherever they are now. So the GSI currently does use foundation temperature as a control variable. So when you get an increment from the GSI, you do get an increment for foundation temperature, which is something that we have to think about and how are we going to use that increment. Sorry, yeah, the GFS version. That's right. But that's the only system that will be initialized with GSI. All the rest are going to be JEDI-based. So for composition, we're going to be using 3D bar from a JEDI using the MV3 JEDI interface. For the land surface model, we're going to be using an ensemble OI that will be making use of the JEDI LATKF. And again, that's going to be using the MV3 JEDI interface. For MOM6 and size 6, we're going to be using SOCA, which is the interface mostly to MOM6, but can handle also the sea ice. And I'll give more details as to exactly what we're going to be doing. But so that SOCA interface will also output an increment for temperature, obviously, for the ocean. And that's where the conflict is going to be starting. Okay, so in terms of technical implementation, this is what our global workflow and the bundle of repository kind of looks like. On the left, you have that global workflow, which is the name of the repository that help us put together these DA cycling algorithms, allow us to run forecasts. This is where also we have all the scripting to have our task implementation for not just JEDI, but a bunch of other things, obviously. It does handle some continuous integration, although it's not great yet, but they are working on it, or we are working on it. And so that global workflow interacts with the UFS. This is the forecast model that the global workflow is working with. And then on the right, you have a subset of the JCSDA repositories. So you have all the JEDI generic stuff with OOPS, YODA, UFO, and I guess you know all that stuff. And then between JEDI and us at EMC, you've got the model interfaces, so SOCA for MOM6 and CIRES, and MV3 JEDI for the atmosphere. And now we have a new interface between JEDI and the global workflow that Corey mainly put together, Corey Martin from EMC, that we call the JEDI app. And this is what Tom and Yannick have been referring to as the last mile implementation of the JEDI. That contains mainly YAML files and all our C-test for the implementation in the global workflow. And as I do usually, I just copy-paste this C-test on my presentation. I don't know why, maybe it makes sense, but we do have a significant amount of testing of all these tasks that the global workflow is running. And it does allow proper implementation. It does allow to invite developers to contribute to our code. So it does work, and we did put a significant effort into putting that thing together. But it does work, and it does allow us to work more efficiently. Okay, so in terms of what we're going to do for JEDI SOCA. So the algorithm and cycling there's nothing amazing about it. We're just kind of following what the atmosphere is doing. It's going to be a hybrid ensemble bar, 4D of X, but 3D background error. I don't think we need to have a 4D background error, although maybe I'll be proven wrong. We are going to follow the cadence of the atmosphere, so 6-hour DS cycle. We're doing 3D IAU for MOM6. Size 6 will be direct insertion because we don't know how to do IAU with size 6. And fingers crossed, we should have 80 ensemble members for both ocean and sea ice at full resolution. And the perturbation will be coming from the LDTKF. I have a schematic of the deterministic cycling on the right. It's showing saving backgrounds at every 3 hours. It's not set yet what we're going to be doing for the ocean. It's going to be either 1 hour, 3 hours, 6 hours. We'll see. Yeah, I guess I'll go on to the next one. Okay, so in terms of observations, it's going to be a little challenging. The table on the right is showing the observation latency for most of the OBS type that we're using, from SST, altimeters. ADT stands for absolute dynamic topography, sea surface height. In situ profiles, in situ SST, so from ship, drifters, or sail drone. Ice concentration, ice freeboard, which helps you constrain the thickness of sea ice. Sea surface salinity, which, okay, no comment, I guess. And so you can see for SST, which are all retrievals, there's a latency of 1 to 3 hours. That's fine, that's great. ADT, the latency is 12 to 48 hours, very likely at least 1 day. In situ profile from 4 to 7 hours. So the summary of that is the early cycle will have enough observation to constrain the mix layer, to constrain the sea ice extent also, but we'll have no altimeters, which means no ways to constrain the mesoscales, and no sea ice freeboard, which means no way to constrain the thickness of sea ice. It's a little problematic, but okay. So late cycle, which is done a little later than the early cycle, it's the same story where we have SST observation, probably a little more, maybe a few more in situ observations, but still no altimeters and no sea ice freeboard. And so we do need to, well, obviously we have to constrain the mesoscale of the ocean. There won't be a good SST boundary conditions in the forecast if we don't have the mesoscales right. So we do need to find a solutions. And the good thing is mesoscale features in the ocean are what you would consider the slow frequency process. So with that in mind, you should be able to get away with a simple 3D of X maybe. And we'll have some engineering solution that will probably work. So one of them is just to do a 3D of X. The other is to do a 4D of X with a much larger window that will be kind of overlapping, which, you know, that might be an issue too. Okay, in terms of background error, we've done quite a bit of work over the past few years. See, my slide is a little messed up. This work does involve people from, obviously, the JCSDA with Travis and Kriti, who are putting a lot of work on the real ensemble B matrix and we're hoping to just steal that work from them. And on our side, we've been spending probably too much time on trying to find a good static B. So that work is kind of distributed, and I think I'm fairly confident that we'll get something that's very reasonable. So I'm not going to go into the detail of our B, but we're working on the static B that will have multi-scales, one for very small scales, which is usually for all the stuff that's in the mixed layer, and then large scales that will derive probably from a climatological ensemble and then the dynamical ensemble. Oh yes, and our static B, it's static, but currently it's being updated every 5 days. Okay, so in terms of what can be done, and that's the result of a lot of work from a lot of people involving definitely that SOCA team, obviously the JEDI people too, and our group also at EMC. We do some work as well. And this is showing, I think, where we are now and why maybe we should be smiling and there are a lot of issues and I'm not going to show any of them. But this is a good result, and this is what I'm showing it. And this is, so on the top left, you're seeing an objective analysis of sea surface height from Copernicus. So it's a level 4 product that we do not assimilate. You have ORAS-5 on the top right, UFS NODA, that's just an ODA run, just a forecast forced with the atmosphere on the bottom left. And then you have that JEDI SOCA run with the UFS. And all of these are based on a UFS with, not all of these, sorry, the bottom one are based with a UFS that is only MOM6, size 6, and data atmosphere. And so you can see that on the bottom right figure looks a lot like the top left figure, which is great. I'm not going to bash or say anything bad about ORAS-5. I'm pretty sure they have a design decision as to why they would not constrain to altimeters as much as we could be doing. But anyway, so this is a good news. We can do a proper mesoscale constraints with that SOCA system, which is great. So in terms of system optimization and experiment design, it's something that we've been trying to put together for years with Travis when I was at the JCSDA, by myself when Travis wasn't there yet. I guess I wasn't running anything, so maybe not. Just with Travis when I was at the JCSDA. And the idea is you cannot develop a system if you can't measure yourself against either other group or a benchmark that you have from somewhere else. So this is work, by the way, done mainly by Russ Treden, Corey Martin, and myself at EMC, where we decided to sit down and do these design experiments. And so we're going to start by copying that golden period that the JCSDA is running, I think, with SKYLAB. So that's that August 2021 JCSDA golden period. We will have an atmosphere only, JEDI-based, that Russ is responsible for. It possibly started. Knowing Russ, it's very possible. And if not, it's going to start next week. We'll have a weekly coupled DA prototype of the GFS V17, which may start next week. We'll see. And an all JEDI-based weekly coupled DA system, which I don't know when we'll start that one, probably sometime this summer. So that's the first plan. The second plan is to have a near real-time system running, probably, at least for now, just the weekly coupled DA prototype of the GFS V17. And that will start as soon as we actually have observations for the ocean. There's currently no observation processing from the NCEP data tank to these 6-hourly tanks that we need to have. So that's the plan. In terms of, so our prototype for the GFS V17 is very simplistic. It's for the atmosphere, it's just a 3D var FGAT. The obs are whatever the obs are for the atmosphere. I do care, but did not put the list. For ocean and sea ice, we're doing a 3D var FGAT. We simplified the B matrix to its basic states, and that was mostly because I was very sure that the results would be terrible, and it didn't really matter what we would be doing for the static B. So it's only constraining the small scale of the ocean. And the hubs were only altimeters and SST and the ice concentration. This was done because somebody at the JCSDA had the idea of changing the names in the UFO and YODA. So I was late to process all the observation, and that's all I did for that time. So just 3 hub spaces. In terms of results, this is looking at the atmosphere, innovations, statistics for radio zones. I don't know anything about it, but Kathy Thomas told me it looks great. So I trust her, that's great. So the more important stuff now, the ocean and sea ice. So in terms of sea ice, the left figures are showing innovation statistics for sea ice concentration for the Arctic and Antarctic. We started that run from initial condition that we got from a 6 months reanalysis that was done previously with that SOCA-Science workflow that Travis and Kriti maintains. And so we started from that, and we just ran that weekly coupled DS system, and oh wow, the statistics are looking a lot better than they used to. There's several reasons for that. One of them is we changed the background error, which it was about time. I think we were 5 minutes. Nice. Yeah, it was about time. We were using a constant everywhere, especially constant background error. So we changed that, made it a little better. In terms of initialization also, we did not, so sea ice is a little special. We did not know how to initialize when you did not have ice in the background, but ice in the analysis. We did not know how to prime in new ice in the model. So we did learn a few months ago, and I think that's the bottom right figure that's being shown here. And I think a lot of the results, that the reason why these results are a little better than they used to be is probably because of these 2 factors. Possibly also the atmosphere is quite a bit better, but we did not try to understand exactly why yet. We will, but we don't know yet why. The second figure is one that Daryl talked about. So you've seen that plot already, and that was very surprising. It's also a little confusing, and I'll get into it later. But so there's a bunch of lines. I've got, I guess, 3 minutes now. I think I can go through them. The blue one is the model that we've been running for the past few years. So that's a model that Travis, well, maybe not Kriti, but Travis probably ran it. That's the UFS with MOM6, size 6 only, and the data atmosphere using CFSR as forcing. And these are comparing sea surface temperature to OSTIA. So OSTIA gives you a daily average foundation temperature. So the way we've been comparing that is just averaging over 24 hours our experiment, sea surface temperature to OSTIA, and this is what these plots, these lines are showing. So mean absolute error from 60 south to 60 north. So the blue line is the worst. That's CFSR forcing. The red line is running the couple model and only constraining the atmosphere with GSI. And that looks a lot better than that blue line. So yeah, great. Now is that orange? That orange line, which we call benchmark from the JEDI-MOM6 data atmosphere system, that was our previous best configuration, best run. We thought, well, I don't think we'll be able to do better than that. We've been stuck at that level for quite a few months. And the green line is what happened when we ran that weekly coupled DS system. And oh, surprise, it's a lot better than what we've been doing in the past. And that's the most significant improvement that we've seen ever, I think. So that was a really nice surprise. But it'd be nice if I would stop there and, oh, it's all great. But it's not, because, so you look now at statistics on the atmospheric side. And so you look at the top left is showing mean absolute error of air temperature of the minus background. This is taken from ships. That work was done by Andy Ekman, by the way, and I probably should have written his name here. And that's for measurement below 10 meters, I think. And so blue is no DA, orange is with ocean DA, and green is what you get in production. And you see that, oh, I forgot something. Let me go back. Sorry. Going back to that foundation temperature, the pink line is what you get in operation. So this is the current system, the pink line. The green line is what we're producing from a lower resolution model. I've got 1 minute left. Okay. All right, I'm going to stop here. The rest will take too much time to explain. But yeah, in conclusion, it could be worse.
Thank you, Guillaume. Maybe we don't have time, but maybe just one very quick question. No, I have a very quick question. Maybe I missed that from your presentation. What's the challenge of assimilating altimeter data?
Oh, so altimeter it's not a diagnostics, but don't really care about that. Just sea surface height. So altimeter measures sea surface height, kind of. The challenge is you don't just adjust sea surface height in the model. What you need to adjust is the density profile of the ocean. And so there's a million ways to do this, to adjust density so that you match some sea surface height. So the challenge is to get that density update correct.
Okay, thank you. So let's move to the next speaker, Hamideh. Did I say it right? I think it's an online presentation.
Yes.
And
Right.
I see you're ready. So the talk is Progress Towards the Assimilation of Ocean Color Radiance Data. Take it away.
Okay. Good morning, everyone. Apologies for not being there in person today. So my name is Hamideh Ebrahimi. I'm a project scientist with JCSDA. I joined NASA GMAO in 2018 in support of JCSDA. Today, I'm going to give you a brief report on our progress toward assimilation of ocean color data. And this is a very collaborative project, and there are so many people involved in this project. My main collaborators are Cecile Rousseau from NASA Ecology Lab, Travis Sluka, Dan Holdaway, Zhao Lu from NOAA, Lionel Artiga from NASA, and Guillaume. And the whole JEDI team collaborated in this project in some way. So here you see the components of the SOCA at the air system modeling. SOCA should be flexible to work with other models as well, but we focus primarily on using MOM6 for ocean, SI6 for sea ice, and BLINK for the biochemistry. So SOCA aims to develop DA for these components, and in addition to interaction between them and atmosphere. By having all these components, we can make progress toward coupled DA. So initial work has been done to do the coupled HAFS for microwave and infrared instruments using CRTM. So for microwave, we looked at GMI and SMAP, and for infrared, we looked at AVHR result, but it was done in kind of hacky way. Now having the generic HAFS using the OOPS, we are going to go over coupled HAFS later on. But here our focus in this presentation is like using OSIM for assimilation of ocean color data, and our main focus here is assimilation of PACE data. Then later on we are going to do VERS and MODIS as well. So what is so this is PACE. PACE is plankton, aerosol, cloud, ocean ecosystem PACE. Our main focus currently is an PACE mission because it's kind of a special instrument and its improvement over the last satellite missions. So thanks to Cecile, we were able to see actually PACE satellite before it gets ready for launch in January. It's currently in NASA Goddard Space Center, and this picture actually is from NASA PACE gallery. And we took some pictures, but we are not allowed to share. So PACE is going to help advancement of ocean biochemistry science using higher spectral resolution than previous missions. And the ocean color instrument in PACE will provide hyperspectral radiometric measurements between 340 to 160 nanometer. And also PACE is going to have better atmospheric correction because of the polarimeters that it has. So So here you can see what is so special about PACE. So you see from the left, the previous satellite mission that we had CZCS from 1978 to 1987. It had just four channels. Then we had CVIFs that it had like 8 channels. Then we had MODIS and VIRS that they had just limited number of channels. But PACE had like more than 200 channels, and it's like previous missions were like multispectral, but this mission is hyperspectral. And this is going to, for example, the near band, we have like more, the visible bands, we use it for ocean color. And the near infrared band, we are going to use it for atmospheric correction. And because it has more band in both visible and near infrared, we are going to have better atmospheric correction, and also we can extract more information for like particle size of phytoplanktons and the more properties of the phytoplanktons here. So our goal is to develop a framework to assimilate PACE data and hyperspectral water living gradients. Here you see the structure of NASA Ocean Biological Model, which was implemented in GMAO. There is an ongoing effort to integrate NOBM to GEOS right now by Mike Mehari. So, but there isn't currently a working tag of NOBM with an OASIM with GEOS. So the NOBM OASIM was run with different physical model like Poseidon before, but not MON5, but we are going to have a structure like this. So the biochemical, so here the green, you see the biochemical model, that is NOBM. Yellow one, you see the radiative transfer model that we use OASIM, that we are going to explain that we implemented OASIM in JEDI. And the circulation model is going to be MOM. So currently we have MOM6, but we are going to run it with MOM5. And the data, the input data that we get for the model is that we have the forced data by satellite, that we have cloud aerosol, and we have the analysis product also that we get wind and humidity from that. So NOBM is coupled to ASIM to simulate the propagation of downward and upward spectral irradiances in atmosphere and ocean. So here it shows that in the atmosphere we have CO2, ozone, oxygen, and water vapor. So everything either absorbs or scatters the radiation that it gets, and we have like coefficients for all these components of atmosphere and ocean in the OASIM. And here ED shows the direct downwelling of irradiance, and ES is the diffuse downwelling. Then we have scattered, the reflected ED and ES, and in the sea also we have the like downwelling, upwelling, and the reflected upwelling. And what is important for us is the water living gradients that we are going to calculate using OASIM here. And also all these things are going to be calculated for each frequency band, but their resolution here is 25 nanometer for ED and ES. So in order to simulate the upward-downward radiances, we need to know the optical properties of the ocean component. Here you see the spectral absorption and scattering coefficient of the common phytoplanktons group, seawater, and the organic materials that is in the seawater. These data are also included in OASIM in a lookup table and with a resolution of 25 nanometer. So here you see the architecture of the OASIM that has been implemented at GMAO. We got this package from Cecil Russo, that was our main collaborator here. She helped me to understand what's going on here and what are the bits and pieces of the software, and also helped a lot with the understanding the what are the these variables and long name of these variables, so we could implement this in UFO. So this package initially was integrated with NOBM, so we were able to clean up the codes and they reformatted and create a repository for OASIM. A special thanks goes to Dan Holdaway, who helped us to make the repository for OASIM. Also, the issues, there were several issues with that. One issue is like the output of the OASIM was just the total radiance and absorption of the quanta with the dissolved organic matters, but we needed the radiances as the simulated radiance at the output, so for each frequency. So we saw that we have all the pieces to calculate the water living radiances. So we added the function, modified the other functions, added another subroutine to calculate the water living radiances. Also thanks to Cecil to understand this part as well. And so yeah, now we have the output of the hyperspectral water living radiances out of OASIM. So everything is ready to calculate h of x using OASIM now. So this is the building block of the SOCA that probably you saw before. So we have the generic JEDI part, and we have SOCA feature that models that they are interfaces that interacting with the JEDI generic part. So what we have done, we just added OASIM as a repository that it communicates with UFO. We wired it to UFO, so UFO can connect to OASIM, get OASIM, also get OBS and GEOVALS, calculate the water living radiances, added a test in UFO that so we can test the h of x using the input data that we have. And for because we don't have it hooked up to the model yet for the GEOVALS, so we got some just value files for example, from NOVM model, we got some data, we got from MERA, the other data that OASIM needs, created the GEOVALS file, and then using the synthetic pace observation, we tested the system. So the summary of our progress is like for the observation for YODA, first we need to convert the input data to the YODA format. So we created the YODA format for the PACE data using the synthetic data that we had. It is very limited data, but we already created the converter for the ocean color. Here you find it in the YODA converter repository. We have another converter for radiance data for PACE. Also, we created a new repository for OASIM. You see the link here. We added OASIM to the UFO. I put it where it is located. And we modified OASIM to compute the hyperspectral water living radiance. And also, we added a test for PACE data. So here you see an example of we just had a few, as I said, we just had a few samples of synthetic data for PACE. Using them, we created the YODA converter for radiances and ocean color data. Here you see the PACE mass concentration for chlorophyll for 1 day for data of 2019, March of 2019. It's just full day for 1 day of 22nd of March of 2019. So here you see the simulated result out of the test for another day. It's like, so the only data that we have for the radiances right now is the March 21st of 2022. So we grabbed this observation, converted the data to YODA format for GEOVALS, but we had the other set of data for 2021, but this is for just test, and this is very preliminary results, just the proof of concept that the system is working. So you shouldn't expect something really meaningful out of this, but it looked much better than we expected actually. So this is simulated remote sensing reflectance that it is directly related to water living radiance. So it's like water living radiance divided by a constant, you get the remote sensing reflectance, and this is a fundamental quantity to be derived for ocean color sensors, and usually they provide remote sensing reflectance retrievals in another file that we are hoping to get these data later and compare our input, our simulated result with that RRS, but for now we can compare it. So yeah, so but we compared this with the old result that CC provided for 2014 data. The patterns look good actually. So at least the peak and lows, look at the patterns of the chlorophyll and everything. It kind of matches the result. But we were testing the OASIM to see what is going on for this constant that we divide the hyperspectral radiance to the extraterrestrial solar flux. So this constant, we have two sets of actually data sets for it. So there is one, the ocean community, we realized there is two data sets. One that is used in the OISM is from the Nickel and Labs publication from 1984. This is really old. This is the blue one you see. This is the solar flux from that publication, and this is the new one. Actually, the red one is the Tulier. I don't know if I pronounce it right, but the red one is the one that currently used in the community, and they advise everyone to use this one. So as you see, there are at some point there are matches, but it's like here in the visible band, especially in 400 nanometer, there is really big, huge differences between these. So we are going to use Tulier instead of the Nickel and Labs later. So, but here I show what is the difference of using these different extraterrestrial fluxes. So off one is currently the one that we already have is ET from the Nickel and Labs. And the lower one is using the ET from Tulier 2014. As you see, it's like almost the peaks are like the results are going to be half of the results of the one that we use using the ET. So this is one thing that we are going to work on it. So the future work is like we are going to replace the ET based on Nickel and Labs with the ET based on Tulier, but the issue is like there are several issues. It's like the data that we already have is like 25 nanometer resolution. And we just have the OISM runs for just 33 fixed bands, and with PACE we have like more bands. We have like 200 bands. So it's like OISM is not kind of able to simulate all these bands currently, so we are considering to see if we can increase the resolution of OISM, but it's not just these extraterrestrial flux data. There are other coefficients that we have, so we want to see if we can just interpolate them or we need to do other stuff. So the next work would be also, we are going to demonstrate OISM with coupled SOCA FE3 blink with SKYLAB. When we have NOBM ready, we are going to run it with NOBM as well. We are going to validate this system using the large data sets that we have available, like MODIs and VERS, but they don't have all the bands, frequency bands, but PACE. So actually, if we run it for PACE, then we can run it for all other sensors, because it's like PACE has all the other frequency, but it's not vice versa. If we validate it for MODIs, it doesn't mean that it works very well for all the bands of the PACE. But this is the way we can validate the system right now. And we are going to add quality control as well. So thank you. So you can reach me by email, or you can talk to Travis in person there. He's going to give me your feedback. Thanks. Any question?
Thank you. Time for a very quick question. Any question online? No, so I have a very, very quick question. Thank you for a very nice presentation. So what's the timeline? I guess there's still a few weeks and things to do. What's the timeline to implement this into the operation system at NASA? I guess that's the plan, right? This capability?
So the PACE is going to be launched in January of 2024. So we are hoping that we have everything ready by then, but there is still a lot of things going to be done. So, but yeah, hopefully by beginning of 2024 we have everything ready. But the first deadline would be end of the first quarter. We are going to have it like ready for testing with MODIs and VERS.
Thank you. So let's move to the last speaker of this session, Yongzuo Lee, and the title is Preliminary Results of JEDI SOCA-Science 3D VAR Applications to HAFS. And I think it's also an online presentation, and I see you. Go ahead and share the screen. Yes.
Can you hear me?
Yes.
Okay.
Can you? Oh, yeah.
Today I will talk about the Mom 6 SOLIDIVA for the HAFS coupling. So this work was done at EMC in collaboration with JCSDA, AOML, and the University of Oklahoma. So outline. So it contains the SOLIDIVA and the results and some summary and the feature work. So the motivation is the model of the ocean state, like ocean temperature, ocean salinity, especially ocean temperature, is very important for the tropical cycle. Okay. So the goals for this work is to obtain the beta ocean states through data assimilation of ocean observation to get the three-dimensional ocean temperature and the ocean salinity, and also the sea surface height. So after we have these beta ocean states, we will use these analysis as the HAFS MOM6 coupling. MOM6 model input. So HAFS coupling has MOM6 model. So we use the 3D analysis as a model, MOM6 model input. But actually, I think, in my opinion, there's two options. One is ocean state, and one is coupling input. So here is the MOM6 SOLIDIVA system diagram. So first we can see the MOM6 forecast on the SOLIDIVA starts from the lot of input. So the color I see is from lot of the input, from lot of the collected data. So lot of the operational and a lot of the observation is also operational. So it will be very convenient for the MOM6 SOLIDIVA to be run for the real time and then provide the HAFS MOM6 coupling. That is also for real time. So it means it is very flexible, not just a research system for some historical case, but it can be used for real time. Okay. So anyway, SOLIDIVA, one is lot of one is SOLIDIVA, one is HAFS carbon. So we configure the SOLIDIVA like this one. So we use ocean observation. We have a MOM6 model. We have GFS forcing, and then we do the SOLIDIVA 6 model. So here is an example of ocean observation coverage. We can see the SST, the SSS, and the SSH, and the insular TC, TS profile, temperature and salinity profile. The TS profile is vertical distributed also. So here is an example for the SOLIDIVA captured the low SSS that is less than 34 ppd, that is the mean CB and the American river amount. So So we can see from observation, we see the green and the even blue color. This is 34 ppb. So it is low SSS. So in the middle panel, observation is in the left panel. Actually, in the middle panel. So we can see in the oval or circle. So we can see the Sluka captures the low SSS that has the liver mass. You can see the color is green, even blue. You see several levels of color indicating the low SSS as the observation is the left panel. Yeah, but on the right panel, the background a lot of didn't capture the low SSS, so it can show the even yellow color. Yellow color means it is larger than 34 ppb. Yeah. So the low SSS that liver mass. So the MOM6 modeling people are very interested in this feature. Modeling MOM6 modeling people. So also we check the sea surface temperature. So the left panel is OBS. It is OSHA composite. Yeah. So we can see near the Cuba, south of Cuba or west of Florida, and then the Bahamas Island, we can see the warmest is larger or higher than 30 degrees. 30 degrees is a very important criteria. 30 degrees. So in the middle panel, we can see Sluka captured as the warm SSD in south of Cuba, west of Florida, and Bahamas Island. So you can see the color is orange, deeper orange. So it means the same color as in the left panel. So it means the Sluka captures the warm SSD in this time. But meanwhile, a lot of spectrum captured a little warm SSD that is larger than 30 degrees. But the area is small. So this situation is not an accident at this time. I checked the warmest for this area during this time for even maybe 6 days, 7 days. So the warmest is persistent. Warmest is persistent in the observation and in the Sluka. So after we have the Sluka analysis, we put the Sluka analysis to the HAFS coupled system. So here is a diagram of HAFS MOM6 coupling system. So in order to evaluate how MOM6 SSP affects the HAFS, the FV3 atmosphere model inside the HAFS system. So we did two experiments. The first experiment called MOM6 a lot of, so it is control run. It use a lot of interpolated data as MOM6 model input. Initially inside the HAFS carbon system. And the second experiment is MOM6 3D. So the name we name it as EXPD. This one uses 3D analysis as MOM6 model IC inside the HAFS. So just two experiments. One is use a lot of model MOM6 model IC, and the other use 3D as model MOM6 model IC inside the HAFS. So we can. I want to explain it because some people may be confused. So then we calculate the difference of SST between the two experiments, as I described in the last slide. So the difference, and also the difference of 2 meter. Oh, it should be 2 meter temperature. I missed the one. 2 meter temperature. I'm sorry. Okay. Here is the 2 meter temperature. 2 meter temperature. Sea surface high temperature. So we can see mostly the difference for SST is warmer, is greater than 0. So also the 2 meter temperature difference is also warm. It means if we have warm SST from then we will have warm 2 meter temperature. It is because the 2 meter temperature is directly affected by MOM6 SST. So this means the carbon is collected. So if we look at the detail and the pattern, so the difference of 2 meter temperature, we compare the pattern is almost exactly the same as the difference of SST. So it means MOM6 3D analysis is used by MOM6 model inside the HAFS collectively. So then we performed a number of HAFS coupling cycles using the 3D analysis and a lot of spectra for the comparison. So this is very preliminary results because we need to do more. So from the statistics of 13 cycles, actually 26 cycles, because we have cycle for 3D and cycle for a lot of illustrators. So based on these cycles and the statistics against the NHC check and intensity. So I just think it's reasonable, but we needed to improve it. So summary. So during the last 2 years, we built up a regional MOM6 radio system that can be used for real-time application. Real-time application means I can run this system anytime until today. So if you ask me to run it today, I can run it today because this radio system is based on a lot of operation system. A lot of operational is running every day. So the MOM6 radio analysis can capture local warm SSD and local warm SSD and low SSD. So we emphasize that warm SSD and low SSD because those are very important fields. The ocean people are very interested in. So of course we performed some a number of HAFS coupling cycles using 3D. So we will test more HAFS coupling system cycles for using this 3D. So anyway, I want to express my special thanks to Dr. Shih-Wei at EMC. Yeah, he helped me a lot for detailed comments and decisions. Though he is not the coach, he is not my leader. So I thank him very much. Thank you. That 20 minutes. Okay. I would like to take any questions from you now or comments from you. Definitely. I'll finish my talk.
Thank you. Are there any questions? The audience or on the chat? No. Okay. Thank you again. Let's thank all the speakers from this morning's session one more time. And now we're going to head into the break, but first, picture time. So I don't know if there's any announcements where to go.
All right, so welcome everybody. My name is Tara Ladwig. I'm the session chair for this next session on atmosphere, land, and coupled applications. We have several great speakers in this session, and we'll go ahead and get started. So first we have Jake Liu.
Good morning, everyone. My name is Jake Liu from NCAR M-Cubed. First of all, I want to acknowledge my co-authors at M-Cubed. They grad already in tomorrow.io, but I don't want to mention that too much. So I also want to acknowledge U.S. Air Force funding to support this PANASI project. And of course, JCSDA core teams and also partner groups. All groups contribute to the JEDI development. I'd like also to especially thank Chris Snyder, who initiated PANASI project about 5 years ago and had trust on me to lead the project team for doing MPAS data simulation with JEDI. And by the way, the global side mostly funded by PANASI project. The regional MPAS JEDI is mostly NCAR internal funding. So let me start by looking back a little bit. That's for about 4 years ago. That's last in-person meeting. Okay, in DC area, I believe I remember. So this one slide I borrowed from that time my presentation. So at that time we already be able to run some cycling, but this is my original remarks there of successful with some crashes. Okay, at that time it's unstable and, there were some problems and low resolution and no reading state. So, but we had some success that time. So where we are now with the latest MPAS JEDI. So we can do deterministic analysis using 3D bar, 3D 4D EMR, or the hybrid mode with dual resolution capability. And the multivariate static B modeling basically follows Wolf DHSI approach. For example, we also have the Psi-Chi to UV transform. And the spatial correlation localization that's realized through BOMP. That's developed by Benjamin Ministry in JCSDA core team, JEDI core team. So ensemble DA, we can do EDA. Yesterday, JJ Grant already talked about this. And he recently also enabled LETKF for MPAS JEDI. So even though we didn't extensively test that function yet. One nice thing with MPAS JEDI is that MPAS JEDI does the analysis directly on MPAS unstructured grid. So then you can do uniform or variable resolution mesh, global or regional mesh. It's fairly easier, easily, and there is no need, to transform back and forth between unstructured grid and the structured grid before or after analysis. Okay, and also I should mention that latest code is much more computation efficient. So that's why I can present you today with some high resolution result. So the part of reason we are doing MPAS data simulation based on JEDI is that we want to leverage comprehensive capability enabled by JEDI UFO, mostly that's already hooked up to both CRTM and RD12. So far, we mostly using CRTM for radiance data simulation. So we also contributed to JEDI UFO with a RD12 C++ interface. That was developed by myself a couple of years ago. So the JEDI UFO, their comprehensive capability, you can simulate a lot of more sensors, but so far here is a list. Basically, we already experimented with cycling experiments. For clear sky, mostly a MSOA temperature sounding channel, MHS 3-volt vapor channels, and YASI also temperature volt vapor channels. So we're also doing all-sky approach, all-sky satellite radiance DA. So in that case, we will include mixing ratio of hydrometers as part of analysis variables. We already demonstrated MSOA window channel and MHS volt vapor channel, ABI HI volt vapor channel, and more recently ATMS. Jun Ban in our team has a poster there. We also use a variational bias correction for both clear sky and all sky radiance DA. And GNSRO, we are switching, yesterday, JJ Bright also talked about that we are switching from refractivity to bounding angle. Even though this talk mostly based on, we're still using refractivity for some early result. Okay, we have run a lot of experiments, cycling experiments, but, there's too much to show. But here I just want to showcase you a bit impact by simulating MSOA window channel over water. That's in a relatively modest resolution, 30 kilometer. So here I will show you some results. 2 6-hourly cycling experiments, full resolution hybrid 3D inverted benchmark. There are no radiance state plus MSOA sounding channel, temperature sounding channel, and MHS channel. There's all clear sky approach. And another one further add all sky window channel from MSOA over water. 6-hourly cycling for over 1 month period. Okay, I list some configuration information here, but I will not go through one by one. It mentions that this is using 80-member EDA ensemble produced by JJ. Yesterday I mentioned this at 60 kilometer. So that's a dual resolution configuration, and we apply VAR-BC. And also there for all sky data simulation, we need a so-called situation-dependent all sky observation error model, or also so-called symmetric error model. Okay, I'm not going into detail how yesterday Greg Thompson gave some equations there. But basically, what we do is that we fit O minus B statistic as a function of cloud amount predictor. Cloud amount predictor could be different measures for different sensors, but for this MSOA, we basically use the cloud leaked water path retrieved from channel 1 and channel 2 spread temperature as a plot predictor. So basically, the black curve is the fitted stepwise function to give you the all sky observation model. So basically, when you have a more cloudy situation, the observation error will be increased. Okay, just quickly show you some result. So after cycling for 4 months for 2 experiments, then we run the 10-day forecast, then we verify against the GFS analysis. That's still a good standard, with operation. So basically, you can see that upper 4 panels is the surface variable, lower is the 4 upper air variables. So basically, you can see the negative, that's root mean square error reduction in percentage relatively. So you can see, for moisture field in day 1, you get about 5% improvement, and then last up to 10 days. that from the MSOA window channel outside data simulation. And, certainly the impact is not uniformly distributed over tropical region. There are a lot of more clouds, so we have a larger impact, up to 10% for day one. Okay, if we verify against independent AHI reading state, clear sky and all sky pictures, we also see the consistent improvement also up to here I show you 6 days. Okay, from day one, 4%, 5%. So upper panel is the water vapor channel, and lower is the cloud sensitive channel for clear picture, partly cloudy picture, and fully cloudy pictures. Okay, that's so very nice impact, and very large impact on the precipitation forecast. Here you can see the all-sky MSOA impact on precipitation is the gap between the blue curve and the green curve. Okay, there are other our paper shows this as the early result. So jump to some high resolution. That one is 30 kilometer. So I recently ran 2 experiments with this still 6-hourly cycling, pure 3D EMR, but move to another period because in another period I have ensemble, higher resolution ensemble, 80 member produced by Craigslist using MPAS Dart, but with MPAS Zeta as a forward operator. So one experiment is 30 kilometer to resolution setting. This kind of comparable to current operation, right? Another one I double, I refined to half of the grid size, 7.5 and 15 kilometer for ensemble and high resolution deterministic. So I just mentioned that 7.5 kilometer mesh, we have about a little more than 10 million grid cells. That's quite fairly large. So this one is simulated non-reading state and clear sky MSOA and all sky MSOA over water. So, okay, it's run, okay, that's quite costly. I just have half months. Okay, not 4 months, even though, I'm kind of run out of my allocation. And, but it is both experiments run, pretty, this O minus B O minus A time series, pretty stable, but we observed some degradation from 7.5 kilometer for the 6-hour background when fitting to observations. Okay, that's standard diagnostic all data simulation people doing a similar thing for that is the radio zone fitting to radio zone aircraft and fitting to MSOA and the GNSSRO. So more or less give you same thing. I also produced 1 to 7 day forecast for this half month period from 2 cycling experiments. Tell me the same thing. Okay, 7.5 kilometer is not that great yet. Okay. So, but what to blame for this kind of unexpected behavior? Okay, this model or data simulation did something wrong. So actually, I didn't mention that earlier. Is that okay? We used a mesoscale reference suite, physical suite available in MPAS. Okay, so far for all global cycling experiments. So this one we have a Newtic convection scheme in this suite is not scale aware. Okay, that's because that's not there is no released code for scale aware scheme for this one. So we are using the standard code. So I guess the non-scale aware convection scheme may be the problem for this kind of 7.5 kilometers kind of green zone resolution. So then I try to confirm if something really comes from model. Then I run some co-star forecast. Then I verify against API readings. Okay, so left-hand side is the 2 panels, 4 panel is the non-scale aware co-star forecast for day one and ready scale aware. Okay, we have already scale aware scheme, but it's not publicly available yet. Okay, but you do see something. First of all, no scale aware 7.5 kilometer versus 15 kilometers seem not very sensitive. This is the so I show the bias. Observation minus day one forecast for ABI reading space for water vapor channel and the cloud sensitive channel. But you do see the scale aware give you more sensitivity between two resolutions. Even though not always scale aware give you better performance. For example, you can see over tropical region, it seems there's some larger cold bias. Okay, the one thing to mention globally, my colleague yesterday, Chris already mentioned. So Craig also running global mesh, but with regional refinement over US. So that's he demonstrated. In MPAS, we have another physical street. It's called convection permitting. So he compared convection permitting versus mesoscale street. Demonstrate convection permitting is better in terms of precipitation forecast over US at a 3 kilometer resolution. So let me jump to regional. So regionally, recently I also ran 3 month-long cycling experiments, regional MPAS JEDI, the pure 3D ENVAR, same period, but also using same 80-member ensemble input from at 15 kilometer. Okay, this domain is quite fairly large, covers nearly the 1/20th of the globe. The basic radius 2,800 kilometer. So still 6 hours cycling because this is over US mostly. So I don't include the reading state here. But again, here I use the convection permitting physical suite with scale aware called convection suite. So first of all, okay, check the cycling stability using 15 kilometers. This is very quick. This O minus B, O minus A, again, that's fairly stable. So that everything looks good. And 7.5 kilometer, 6 hour background forecast now fitting better to observation compared to 15 kilometer. So that's not like case I showed earlier for globally. Okay, this one I use the different physical suite with convection scale aware. So there is fitting to aircraft reduction the 4% or 3%. Over this domain. And then if we further down 3.75 kilometer, that's kind of convection permitting resolution. And then we verify against 6 hour background forecast, verify against the ABI channel 10. Okay, we also get the left panel is the root mean square error against water vapor channel ABI, and the right-hand side, the root mean square error reduction or increase. Okay, the blue color means the positive and from 3.75. Okay. Not everywhere is better, but overall is better. Okay, I have overall statistic is better. Okay, just a few concluding remarks. I should say that MPAS model is not really that new. This released more than about 10 years ago. So it has capability to run, convective scale, weather or climate, even climate modeling globally, regionally, or global with regional refinement. Okay, but you need some good computer. MPAS JEDI data simulation. So I should say that almost ready for convective scale data simulation, regionally or global with regional refinement. I think we also close to do DA at 3 to 4 kilometer resolution globally everywhere. And I should say that co-development with JCSDA JEDI partnership is the key for the success. Okay, we leverage a lot of work from other groups. Yeah, so first of all, another point, need to have the model right first, of course, configuration, or you need to improve your model physics to fully benefit from convective scale DA. And we should be able to experiment more high-resolution MPAS data with NCAR's new computer is named the Ratio. In production this fall, there are 20% computing power from GPUs. That's all I have. I can take a question. Thank you for your attention.
Thank you. Do we have questions from the audience?
That was really nice, Jake. Very impressive. Two quick ones. The results you showed for the all sky, those improvements, RMS and FITS, were those global or tropical? Global.
That's the range is global. Okay. The impact is more concentrated over tropical region.
I was going to say, those statistics for the tropics would probably be even more impressive.
Yes, that's
what we would see a lot in the tropics, low level T and Q for the all sky. The other thing is when even with the scale aware codes, are you doing any retuning as you change resolution at all?
You mean the tuning or?
Are you just changing resolution without, I mean, I know it's because even scale aware, it's not necessarily going to be perfect.
Yes, I'm not a modeling person, so I don't know but I'm planning to feedback my result to my modeling folks. So they develop this scale aware in theory, but we perhaps need tuning for
a little bit, because I know just from Bill Putman that in our shop they always does a little bit of to make it up. But anyway, this is really very impressive results.
Thank you for a great presentation and very impressive progress. Several slides back, you had a metric which was an influence ratio. Can you describe that in a bit more detail, please?
Influence ratio, which one?
One where you had a part.
You mean the all sky observation model?
Passed it.
You passed it.
Oh, sorry.
I think scored again.
Which one?
One more. This one.
Okay.
Yeah, the right-hand plot.
Okay.
Can you describe that, please?
Yeah, this is Craig. He often produce this kind of FS score because this neighborhood precipitation modification. So you need some neighborhood. I believe. Yeah, he used one model resolution is around 3 kilometers over US. But when he calculated FS score using a box, maybe 10 by 10, so this 100 kilometer influence reach box to calculate the FS score. Yes. And the larger value means better. So the convection permitting is better, at least over US.
I think we shall move on to our next presenter. Thanks, Jake. Our next presenter is Sarah King from the Naval Research Laboratory.
Okay, hi. So for those of you I haven't met, I am Sarah King from the Naval Research Laboratory out in Monterey, California. I am the lead developer on our JEDI-enabled data assimilation system for Neptune, and I will be giving you an update to the update that Liz Satterfield gave you at the JCSDA symposium back in January. So it is my pleasure to have working with me on this project, Nancy Baker, who you heard from yesterday, Justin Zhu, Bill Campbell, Bailey Stevenson, Francois Vandenberg, and Rustin, both of those two from the JCSDA. And then on our modeling side, Alex Reinick, James Doyle, John Michalakis, Boon Chow, Ed Zaran, and Yongzuo. Okay, so the Neptune Global Forecast Model, it is currently a three-dimensional spectral element model. It's non-hydrostatic model of the deep atmosphere. It was designed for both accuracy and scalability And I have scalability in bold here because sometimes some of the features that provide that scalability aren't necessarily as friendly for data assimilation. For example, this model doesn't have halos. So our target for transition is 9 kilometers, 101 levels, and we will be using CCPP for physics. So an important note for this particular project is the model dynamics and the physics are still under development. So we actually have this iterative process where we're updating the data assimilation, we're updating the model, and we're also updating the physics all at once. I've been told that the last time that NRL has tried something like this was about 40 years ago. So that's my excuse for not knowing what I was getting into. And I'd like to note that the TLM and adjoint are currently under development. So our Falcon data assimilation system is a flexible assimilation linking collaboration to operations for Neptune. And I'd like to emphasize the collaboration because we view our partnership with the JCSDA as a vehicle for us to proceed with JCSDA collaborations and also external collaborators. So the way to think about this data assimilation system is really a blend between our current NAVDAS AR system and JEDI. So what we've been doing is adapting NRL NWP components for use in the JEDI infrastructure and also adopting JEDI components where it makes sense. And the idea here is in a few years, we'll be able to replicate our current capability. So the main things that we've been working on are observations. Right now we're using NRL preps and QC. Eventually we want to move towards JEDI QC. Right now, we're using our multivariate static B that has been adapted from NAVDAS AR. We're doing a lot of diagnostics and verification. This is going to be based on the current diagnostics that we have in NavGem, as well as JEDI-SKYLAB diagnostics and MET+ diagnostics. And currently, we're using Silk 7 for our cycling DA infrastructure. So I want to point out that I do have a box on here for ensembles. We have not started ensemble work. It will likely not start for another year or two. So at the end of the day, we really want to develop, as Nancy mentioned, a unified data assimilation system that is flexible and modular for future Neptune applications, be it coupled ensemble, as I mentioned, limited area, or high altitude. Okay, so observations, current status. So some of the discussion I'm going to have with observations, Nancy had a poster on yesterday, so I will defer to her for any questions that you may have. But the idea here is with the unified system, we also want a unified model agnostic preprocessor that's going to feed our current models. That's COAMPS, NavGem, Neptune, and Navy ESPC. It will handle any decoding, QCing, thinning, superobbing, etc. And we're expecting to get this ready to go by September 2024. For now, in these experiments that I'm going to discuss later, we're basically using observations that have been assimilated by NavGem, and this also means that we're using NavGem bias-corrected radiances for our observed value. As we proceed, we're going to slowly get to less and less pre-processed observation feeds, and we've also been working on getting the bias correction set up for Neptune. So as I mentioned before, we're also adapting NavGem diagnostics or OBS diagnostics, and this gives us graphics to facilitate comparisons between NavGem and Neptune. So I do want to emphasize that Neptune does not have a secondary DA system. This is it. So a lot of the comparisons that we are doing against NavGem, just to get an idea of the general behavior that we should be seeing, and whether we're making beneficial improvements to our analysis. So static B, that's going to be our current operational static B. It follows Daly and Barker 2001 or Zhu et al. 2005. And this is going to give us our hydrostatic and geostrophic balance. What we have here in the figures are one-up experiments that we've done just to make sure that when we did our refactoring work to make our static B compatible with not only JEDI, but Neptune, that everything still works as it should. We also, when we were doing that refactoring work, made our static BGAML configurable. And something to note is we're actually bringing in this error covariance through the Neptune JEDI interface and not Sabre currently. So for our cycling, we tend to do a lot of cycling experiments. We're always checking on the health of the system. Right now, we're using the JEDI 3D VAR solver and the inexact precondition conjugate gradient for our linear solver. This is a little bit old. We usually are converging now, I believe, in more like 110, 120 iterations. So we're constantly running month and multi-month cycling. We're using about 2.4 million OBS per 6-hour update cycle. Currently, we're testing at about 86 kilometers. And we have our initial diagnostics integrated into our Silk suite, and we're working on our scorecard. Okay, so observations, current status. Here's a list of the instruments that we currently are assimilating. AMSU, ATMS, MHS, SMIS, AMSR2, radio sans aircraft, satellite AMVs, and then what we have here on the right are just some increments that we've been getting from this cycling system. We just sort of look at these to look at the overall health of the system, make sure that our increments aren't really growing in time. We have the potential temperature in the left-hand column at 500 millibars and the zonal wind on the right-hand column at 500 millibars. And just for reference, we're ingesting about 52% of the observations that our current operational system is using. And we are expanding our observation pre-processing, and we're about 88% of what is in NAVDAS-AR currently. Okay, so I mentioned before, it is an iterative process between us, our modeling team, and our physics team. And here's kind of a representation of what is going on here. So the first panel that we have there is just for reference. It's our current operational system running a 40 VAR, and it's the 30-day average RAOB global temperature bias. Okay, so the next figure, one over, is about where we were a year ago. So this is with Neptune version 1.2. We had far fewer OBS coverage, and what we were seeing at that point in time was impacts at the top from the sponge layer that was in the forecast model, and we were also picking up the cold bias that the forecast model had. So since then, we've upgraded to first Neptune 1.3.2, and that actually gave us a higher model top. It's now at 80 kilometers. And we incorporated more observations, and we brought in some changes to the physics, and then we were able to improve the bias. What we're looking at right now with Neptune 1.4 is kind of taking a look at the different physics suites that are available in CCPP. So the top figure all the way on the right is our bias doing a month-long cycling experiment with the CCPP physics suite number 4, and under that is suite number 7. And just to point out that the standard deviation and bias are comparable to what we're seeing versus NavGem on the left. So like I said, it's this iterative process where we're pulling in changes to the model, changes that are being made to the physics, as well as changes to the DA system. All right, so this is using MET diagnostics in comparison against GFS analysis. So here we have the Northern Hemisphere. The first figure on the left is the 500 millibar geopotential height. So this is another way that we're tracking our progress. So the top two lines, the cyan and red, that's about where we were spring 2022, so a bit over a year ago. And then you can see we've made improvements to the DA system. So the green line is when we added a hydrostatic column update for the pressure. The magenta line is when we actually started pulling in those surface pressure OBS. So, sorry, the blue line on the bottom is the NavGem 40VAR just for comparison. So, you know, we're slowly inching our way closer, but again, that is an operational data assimilation forecasting system. It's a lot more sophisticated than what we're working with now. So on the right, we have the Northern Hemisphere 250 millibar zonal wind. At the top, you can see where we were about a year ago with the green, red, and cyan lines, and where we currently are is below that with the pink and yellow lines, and then for comparison, NavGem's below. And then to belabor the point, the 1,000 millibar zonal wind is below that, but that figure does include what the NavGem analysis would look like if we were running a single low resolution analysis. So currently our system does not include dual resolution. Okay, timeline. So ongoing. Right now we're actually already cycling with FGAT. Hopefully we'll have some results from that soon. We're also implementing our dual resolution. In this case, we're actually using ESMF to do that, as it is used extensively in the forecast model. And we're also starting to add in high resolution forecasts from the cycling system. So coming forward to the end of FY24, that is September 2024, this is when we expect to hand this over to our operational partners. We're looking at a 9-kilometer grid for the forecast model, 3D VAR for the DA, and then CCPP-enabled physics. And then the outer year going outward, FY25, so shortly after we initially have this transition, we'll be looking at transitioning 4D VAR. After that, that's when we will finally get ensembles in a few years, and then we'll start looking at hybrid 4D VAR, and at this point in time is when we'll probably evaluate what we're doing with our static B. And then FY29, that's when we're looking at other applications, so limited area, that sort of thing. Okay, so the next steps, we want to continue to move towards a less preprocessed data stream. We're going to bring in that flexible API to provide system portability. That's going to also give us the observation decoding, QCing, thinning, super robbing, additional NRL-specific QC filters. Again, add more OBS for the solver. We're working on the dual resolution and FGAT right now, and then we will increase the horizontal resolution or the inner loop resolution, if you will. And we're going to continue to add diagnostics. So just to kind of bring it to a close, the Falcon Unified DA system for Neptune will be JEDI-based. The initial implementation that we're going to be doing is global 3D VAR. And then following on with 4D VAR and hybrid 4D VAR, currently our operational system is hybrid 4D VAR. So at that point in time, we'll have a capabilities replacement. I will mention that we'll be running NavGem throughout this time period. So we've already, as I've belabored the point, we have the multi-month cycling demonstrations of the JEDI-enabled 3D VAR. We're also using the diagnostics that you saw today to help guide our DA development, as well as the model development and physics tuning. And we will continue to upgrade and test the system and perform regular diagnostic comparisons between our Neptune system and our NavGen system. And we will also continue to rapidly bring in new observation types. Okay, so thank you for that. And I just wanted to, before I conclude, thank everybody in the room on the JCSDA side who has helped us with this work. I'm going to call out Dom. So something I should have mentioned too is that we have gone through 6 HPCs in the last 3 years, and Don helped us out with 2 of them. So I couldn't be more grateful because I'm the one who had to do the other 4. So Francois, Anna, and everybody else who's helped us, I'm very grateful, and thank you so much.
Thank you, Sarah. Do we have questions in the room? Maybe while you're, oh, go ahead.
That was really nice. Could you go back to slide 9, please? Okay, so like right-hand panels, just in terms of closing the gap to blue, the differences here are hybrid 40 bar and 3D bar. What else?
Oh, sorry, this is 40 bar, so not hybrid.
Okay, so the blue's 40 bar.
Yeah, 40 bar. We didn't want to give ourselves too tall of a hill to climb. So the things that are going to happen are going to be 3D bar FGAT, so hopefully we'll see an improvement there. The big one is probably going to be the dual resolution. So if you look at the bottom panel, you can see the improvement to the RMSE that the dual resolution gives to NavGem, and that is a big improvement.
What color am I looking at? Sorry.
Black versus blue on the bottom figure. So we anticipate getting a nice reduction in the RMSE at that point in time. But I will also add that this is with an older set of physics suites, and we have a newer, improved set of physics suites.
A lot of moving parts.
Yeah, I'm not going to say.
Data counts are data are different or not in these?
The data counts would be different. Yeah. So yeah, there's all sorts of things going on here. So
lots of room to make up the gap.
Exactly. And again, we're targeting a 3D VAR system, so it's probably going to be a few years after that before we
very nice.
Beat NavGem finally.
We're familiar with moving targets in our model development and simulation development as well.
Yeah.
I was going to ask about the dual resolution part. What resolutions, do you know what that will be, or still?
So we're still not 100% sure what we want the increment or the DA resolution to be. So likely we're at 86 kilometers now. We'd like that to be more like 40. But we have a hard deadline. So it's just going to, I think we can make 40. I guess I should be more definite. We'll make 40 kilometers. You heard it here first.
Okay, thank you. Any other quick questions? Well, thank you, Sarah.
Sergey.
You use the microphone.
What is the timeline for the coupled application?
We don't really have a strong one. Are you thinking ESPC? I'm not sure what the timeline is for bringing Neptune in. So I'm guessing more like in the 2030s, but we don't have a firm timeline for that. I know work is already underway to sort of look into that, but you know, we're not planning on sunsetting NavGem anytime soon.
Yep.
All right, thank you.
Come on up, Sergey. Sergey is our next presenter as well from NOAA PSM.
Well, it was great to see Sarah's talk, and you can see I'm very attached to color blue from my Navy days. So all my templates are blue. This is about building up ensemble solvers in JEDI, especially for the transition to the GEFS system, which is a NOAA's ensemble system. This work is internal to NOAA at this point. It just started a year ago, and it's conducted by OER Lab PSL, where most hands-on work is conducted by Wei somewhere here in the audience today. And on the WES side, it's Corey, Martin, and Travis Ellis who conducted most of this work. And I hope as this project ramps up, we'll re-engage with JCSDA. We have a great relationship with them, and hopefully we can continue it in the next year. And I'll kick it off with a quote from Tom Molinier when he was describing EOP 22. He says that EOP 22 was laser focused on transition of JEDI to operations. So that this talk is about that. So the outline, I'll talk about role of ensemble solvers in a transition timeline. And I'll talk about difficulties we're facing with scalability, not difficulty, but the progress we're making with scalability and scientific verification of JEDI GTKF solar atmosphere. And I'll tell you why I'm focusing on atmosphere here. So many of you have seen this rainbow plot. It's called, so there's no pointer, but it goes, the time goes from right to left, and on the y-axis is different operational systems that we have, and the main idea is that they're getting consolidated at NOAA. So a big transition is coming up in about a year and a half from now is when we go to a consolidated global system, and that's the green boxes, and the consolidated regional system, which is a blue boxes. The orange box is a HAFS system, a hurricane system. So all of these transitions have an ensemble solver inside of them, and all of those solvers are based on some version of ensemble common filter. So the current ensemble common filter is JSI GETKF atmosphere. It's performant. It does what it needs to do. It has an end of life associated with it. It's not going to perform for future applications that we envision. And we want to really invest into JEDI-NKF filter. But at present, it's a JEDI-NKF filter lacks scalability and throughput to match current JSI capabilities. And we are working hard to move that capability to where I think it needs to be. Okay, so I think many of you have seen, we have a UFS model on the left, and it has FE3 DI core, CPP physics, NOAA MP. I think there was some other presentation earlier today that was using NOAA model, an old land model. There is Ocean, MOM6, Ice Size 6, Wave Watch 3, Go-Kart Aerosols, and on the data simulation side, the transition and the next big transition will have still JSI and atmosphere, no data simulation for waves. Land will be done with FE3 JEDI, aerosols will be done with FE3 JEDI, and sea ice and ocean will be done with SOCA. So there will be a big part for JEDI to play in the next transition. But we're still sticking with an old system for the atmosphere. So the transition after that, sometime after FY26 possibly, the main part of the transition will be actually transition into FE3 JEDI. The things that are unclear right now, there will be any data simulation for waves. Will there be any in-core capabilities for this transition after next? And definitely we're looking for new science, because we can't just keep advancing by replicating existing science in JEDI. We really need to start thinking about what other new capabilities we can bring to the table. Okay, so sorry. So the rest of the talk will be more kind of hands-on talk about how we're trying to make the JEDI atmospheric solver, NKF solver work efficiently. So the workforce of comparison will be GTKF solver. So GTKF solver is a solver optimized for simulation of radiances. It's operational at NCEP, and it's very efficient with update to ensemble initial conditions. By comparison, it's the most computationally intensive task that we have. It's about 1,000 cores, or at least this for most of the applications. By comparison, LTKF for the ocean ice and composition is about 100, on the order of 100 cores, and land is in the order of tens of cores. So the workhorse for comparisons will be an 80-member ensemble at 1 degree, and we're simulating zones and MCA from NOAA 19. And on top is a timeline for the one cycle of GSI with all of observations at this resolution. So we're running at a constant 400 core count. That's the y-axis. And you can see that the forecast takes about 33 minutes, ensemble forecast. The GSI observer takes 10 minutes, and GSI solver takes 17 minutes. If the bottom figure shows the reduced set of observations, where we reduce it to zones and MCA, and the total time gets reduced to 44 minutes versus 60. So it's about twice as fast, more than twice as fast for the solver with the reduced ops counts. So the first lesson we'll learn that unfortunately JEDI GTKF is not scaled out of the box. So this is scalability plot. We have node count on the bottom, and we have a logarithm of time in minutes on the y-axis. There is a lot of lines here, but if the program scales, I think it's called weekly scaling here, then you should see those colored lines line up with the dashed lines. So there's a couple of lines I want to draw your attention to. So the total line is red, is kind of flat and on top of a graph. So the next line is a dark blue, it's an observer. And the linear algebra, the core of NKF, is a yellow line and a light blue line. So the linear algebra scales super linearly. As you add more cores, your memory bandwidth improves. So the core of NKF actually works well. Well, the observers are struggling. And the challenge with GTKF, that it observes about 1,000 modulated ensemble members. And it dominates the costs. And the way that it's implemented right now, and not putting all the blame on JEDI, I played a role in implementing it as well. So the way it's implemented right now is that it doesn't scale. It does this observer sequentially. And it's just not enough parallelism in this approach to benefit from increased core counts. So that's the point at the bottom, that the Hamideh law starts to dominate. Okay, so our approach to make it go faster is increased parallelism. So out of the box, as I was describing before, first we run observers, which is serial in members. So each observer is parallel, but you run this job 1,000 times. So all the things that are irreducible start piling up if you do it 1,000 times sequentially. Then we do an ensemble member update, which is inherently parallel. And then for our specific workflow, we were converting from a cube sphere to Gaussian grid, which was again done sequentially in member space. So the things that we implemented for the following figures will be, we parallelize observers. So we have 80 separate jobs, and each one will observe a different member. And it writes out to files. Then the ensemble, the NKF will run in parallel, will output files, and we'll have a conversion program that will convert from cube sphere to Gaussian. So to give you a sense of the type of impact on the wall time that we see, so the top one is about 12 months ago when we were running a single executable. So it was taking 3 hours for a cycle, while our target was 44 minutes. So it was clearly not great. So when we implemented bespoke cube to Gaussian, we shaved off about an hour of wall time. And that conversion is so fast that it's not, doesn't make sense to plot on this graph. It's about 1 or 2 minutes. So about 4 months ago, when we implemented separate observers, now we're up to about 61 minutes of wall time. And we have about 8 minutes in the serial program that glues files together. So what are some of the next steps? So if I'm going to go from green to yellow. So in the solver, we're spending about 3 minutes reading observation files, and we can definitely do better than that. Our ensemble concatenation program needs to be parallel, so we can shave maybe about 7 minutes out of that. Our JEDI ensemble of ops observer, it uses nonlinear observer, and if we switch to using Jacobians, we can probably shave some additional time. And finally, the yellow part, which is a JSI observer, we're considering not using JSI observer by reading directly from buffer files. So that should save us about 3 minutes as well. So another part of what we're doing, we're systematically going through different observance systems. And the observations that I made during these talks today is that we have 2 camps, people who go, we have a reference system and we're going to compare everything to the reference system. And that camp is moving very slowly. And then we have a second camp like MPAS and the Navy that are saying, we're just going to jump into a completely new system, throw all the ops and just make sure it looks like planet Earth. And that camp is going much faster. So we're in the first camp when we're comparing to JSI results. So one thing that we discovered that every time we go through a new observance system, we discover not a bug, but something that needs fixing. So for surface pressure, so top left is a matchup of 6-hour forecast to temperature in, I guess in Northern Hemisphere probably. And you can see that we can reproduce GSI perfectly. There is a, it's as, you know, it's good. Now there's no statistical difference between the two runs. With zones, JEDI is actually better. We try to understand why JEDI is better with zones. We couldn't really narrow it down, but you know, it's good, it's better. Currently we're working on zones and AMSU-A and zones and AMSU-A in IASI runs. And while we're working through all of these things, we're discovering something that needed to be fixed. Surface pressure corrections, direction of vertical coordinates, negative increments to soil states, running out of memory, and things like that. So concluding remarks, so we do find systematic testing and comparison between JEDI and GSI has been essential to find, let's call them bugs, or things that needs to be fixed. So the next year, we'll continue increasing our observance system, add more things. We'll do a code sprint on serial filters with a pathway to a local particle filters. And that will be done together with JCSDA. We'll collaborate between EPIC, JCSDA, and OER to develop partial in-core capabilities for NKF for coupled UFS. We're hoping that there'll be a GTKF inclusion to a SKYLAB release. I understand it's part of the AOP, so definitely be happy to support that effort. There will be also, we hope there'll be an effort between JCSDA and PSL to optimize memory usage and increase parallelism in JEDI, GTKF, and IOTA. So from our cursory look, it looks like IOTA is using about 4 to 10 times more memories than we were expecting for it to use. So for us to assimilate things like hyperspectral sensors or satellite winds, we really need to work through the memory issues. I think that's it.
Thank you, Sergey. Do we have questions from the audience? I did have one question that your bullet there about linking to the local particle filters. Can you say a little bit more about those plans?
Well, so to link to the particle filters, the first step is to have a serial filter in JEDI. So we don't have that right now. So my understanding, talking to the algorithms team at JCSDA, is that we're planning a code sprint to put a serial filter, maybe this fall. And once the serial filter is implemented, then academic community, like maybe John Potter Joy specifically, can take it further and actually put particle filters in.
Yeah, that would be interesting application, but sounds like a little bit more time needed.
I think a year from now is reasonable.
Yes.
Yeah, just have a quick question. I noticed in your workflow, you convert them at the end to Gaussian grids. Is there any reason for that?
Because we don't have 1 week of field pigeons time to use increments on a cube sphere in IRU. But so the reason is we do use IRU, and the only IRU that's implemented right now supports Gaussian grids. But it will be much easier to do it in a cube sphere. We just don't have that 1 week of time to implement it.
Any last quick questions? Good. Well, thank you, Sergey. Our next presenter is Jerry Dong from EMC.
Hello, everybody. And my topic is transition of JEDI-based SNODA into NCEP operational system. I would like to thank co-authors and they are Dara, Mike, Corey, and from EMC, and Clara and Sagna from PSL. Here's the outline. Its background, JEDI-based snow DA efforts, observations, and QC. JEDI-based snow DA transition into operations. And the background, land analysis in NOAA operational GFS system was conducted with GLDAS using the NOAA ISM to involve land states and computer surface classes. Current operation have simple method merging the external produced snow depth analysis with forecast. However, the assimilation of in situ and remote sensed estimates of snow, land surface states such as moisture and snow, and not supported yet. And it's obviously we are far behind other NWP centers. Here is JEDI-based snow DA efforts. The land DA can leverage with the atmospheric DA JEDI efforts because we have the same grid. The JEDI-based snow analysis use OI, optimal interpolation developed at PSL for analysis snow depth from remote sensing, snow cover, and station snow depths. The OI snow depth, snow DA significantly improve the current, comparing to the current operational system, and a small improvement to the 2-meter air temperature. Next slide will show this. And next is transition to the operation requires a near real-time observation data from the GTS. And snow DA currently being added to the GDAS app and for use in the operational system. And here is from the PSL colleagues, and to compare the OI snow DA analysis with the current operational system, and shows a significantly improved snow. And in the right is manually a small improvement to the 2-meter air temperature. And here is JEDI-based snow DA workflow. And in the pink color is show the observations. We use the snow depth from GTS, and IMS snow cover from is a satellite-based. And the satellite-based snow cover and first calculated into the snow depths, and only because this is a daily observation and only simulated at the 18Z cycle. And the JEDI part is in the red, and they convert the observation into the IOTA format, and then assimilate into the JEDI-FRE3 bundle. Use LETKF OI here. And the quality control use the UFO filters like boundary check, domain check, reject list, background check, and body check. And there are some utils, and can create ensembles and calculate the snow depth from IMS snow cover, and also apply the JEDI increment into the forecast model. And we break into the pieces of this and add them into the GDAS app. And the GDAS app, as earlier they mentioned, self-presenter mentioned, and is EMC repository, connect JEDI to the NCEP operational system, and enable easier validation of JEDI components. And here is the snow, for the snow application. And we add several C-tests and for the snow DA. Here's the observation data, and the snow depth shows from the GTS, and there is two types of data. One is in the old format is tag format, and the new format is buffer formats. And first, the duplications will be removed and between the tag format and the buffer formats. And then this observation data will dumped into the GFS and GDAS 4 cycles. And here is the 4 cycles. And you will see, and there is about totally about 3,000 reports in each cycle. And some cycles less and some cycles more. The 3,000 reports available can be used for assimilation. And here we take a close look and see the snow depth values, and we found there is some outliers. And like look at this table, and there is some negative, like 0.1, 0.01, 0.02, like these values. And also there is some small positive values, and like 0.1, 0.2. And also you see the red in the table is like most is some is like over 400 meters. That definitely is bad reports. And we take a close look for this station in the left column, and you will see there is for the negative value is okay, and we can easily remove by the like boundary check, and the snow depth cannot go to the below 0. But for the small positive values, 0.1, 0.2 in the upper left figure, you will see 0.01, 0.02. These values you cannot easily remove. We compared with the surrounding 10 stations, and we see, and there is a very nice snow curves in the other like 10 stations, neighboring stations. But this station, the 0.01, 0.02, if not removed, will significantly biased lower to the assimilation values. We need to remove these reports. I guess for this one, maybe they they try to put the values like -0.01, 0.02 as a missing value, but they forget the negative signs. That maybe causes the problem when they input the data. Take another example for the right column. You will see here is a very nice curve comparing to the surrounding 10 stations. But you will take a look at the vertical axis. You will see the snow depth like to 30 meters. That's impossible also. And I think for this is maybe they forget to do the unit conversion. Maybe this one is like centimeters, not the meters. And here for these bad reports, and we need removed. We need to use the built-in JEDI built-in filters. And here are several filters: boundary check, background check, reject list, and body check. And I just introduced a couple used is body check and reject list. And here's the body check. Body check is a powerful tool and can check an observation is consistent or not with its neighbors. And this method is developed by the UK Met Office, implemented in JEDI, and we can use directly. And for the details, I don't want to go to the details. For the details, you can refer to the Benjamin 2004 papers. And here, when we directly use the body check, and we will find that these upper right figures, and only like less than 60%, like observations can be used. That's not good. And we compare these, like the red dots can be used, but the blue dots is not used in the assimilation. And we compare this figure to the left figure, and for these blue dots is like 0 snow depth. But this 0 snow depth is much valuable comparing to is in the data snow data assimilation. And so we wanted to use this data. And I work with like UK Met Office colleagues and help to fix this problem. And that's the background error issue. And we after fix, you will see the lower right figure, and it shows like over 90% observations can be used in the SNOW-DA application. Yeah. Another is like I tried to calculate the the maximum snow depth for each station over 2-year period, and in the upper left figure. And if we like just consider like over 3 meters, the maximum snow depth for each station is like 500 stations over 3 meters, and over 8 meters is have like over 200 stations, and some stations in the tropics. That's definitely not possible, and we need to remove these stations. Otherwise, will cause large bias. And I try to create some criteria and to filter these stations out. And we just use the first like site criteria, the snow depth over a threshold, and we found like in the mid column, and there are several hundred in the reject list, but that's not efficient. And I added another one, is the second criteria, is the number above the threshold, over the percentage of the number snow depth over the threshold, over the, comparing to the total snow depth data. If this fraction is over 50% and less than 90%, and the second column, the third column, you will see like there is some about 30 stations can be listed in the reject list. This criteria is just under development, and I would like if anybody can have suggestions, and I would appreciate. Here is I conducted some GFS analysis. These configurations use LHT-KF-OI for this day, 4 cycles. And the observation data is GTS snow depth, and model resolution is full resolution. And here's 3 members. And here shows the increment for the GFS analysis. I comparing the LHT-KF-OI in the lower left, lower right, comparing to the other solver in the JEDI, like 3D-WAR and 3D-ENWAR. And it's a similar patterns. You see the snow increment. But for the 3D-WAR is like quite smooth, and the 3D-WAR is like provide more details. LHT-KF provide even more details. I also compare the LHT-KF for the 2 cycle, 00Z cycle and 06Z cycle. We'll see, and the left column is OMPG and the right column OMAN. And you will see the colors, and from the OMPG to the OMAN is like move the colors into the middle, from the dark to the shallow, and get a spatial improvement, and also the statistics is the RMS reduced a lot. Here's the summary. And working with PSL and JCSDA, we set necessary infrastructure, and with JEDI-based land DA capability for using in the operational system. And JEDI IP3 bundle was used to conduct land DA tests, and the quality control, and filter out the poor resolution observations, and assimilation of these can help and reduce the bias for the GFS snow analysis. And this is already in the GFS system for the version 17 and nearly complete. And is under review. And we already added like 3 PRs merged, and the last PR is under review. And the impact of after this implemented, and the impact of snow assimilation and the GFS forecast that we further evaluate. That's all. Thank you.
Thank you. Do we have questions from the audience?
Maybe you have a quality control feature in there that just does station elevation as one of your most rudimentary checks, because So clearly 8 meters of snow at 4 kilometers is more believable than at 0 kilometer elevation. Just wondering if you have a simple check.
Yeah, definitely. Yes, elevation is we are not considered right now.
Okay.
Yeah, but for the LHKF OI and this one has not only the horizontal correlation and have vertical correlation. That one consider some of them. Yeah, that's quite important for the elevation issue.
I've got something that's not exactly a technical question, but you've made a lot of progress, but I'm wondering, have you been impacted by our inability to keep like a core land surface team lead with the Joint Center in the last year? Has it impacted your rate of progress?
You say that response. Okay. It's I don't know. We usually have the weekly meeting and that discussion, but after the loss of the leader and Andy, and we canceled that meeting. So I don't know. Yeah. Do I answer your question?
Jim.
Okay.
Jim in sports, that's called a buddy pass. This is a very nice talk. Can you show slide 17 again? If I have the right one.
Oh. Lost.
It was the one of the increments. This one. Previous one.
Okay.
Yeah, so I guess I was just noticing over Siberia, Northwest, the sign of the increment between the 3D ENVAR. Am I looking at the right thing? Between, say, the 3D ENVAR in the top left, upper left, and the LETFOI in the bottom right, the sign is quite different over a lot of Siberia. Am I misinterpreting what I'm looking at? I see lots of reds, and then I see some blue, like.
Okay, I didn't take a close look for this yet. Yeah, probably. Yeah.
Anyway, just notice that the sign had changed.
Yeah, right. Yeah, and then there is blue, and there is a lot of red there.
Anyway, that's the thing. The other thing, did I understand? So, in terms of real time, most of what would be available would be the in situ obs. You'd mentioned at 18Z there is a satellite snow cover. Yeah, so there is a remotely sensed snow cover product that's available. That will be available in real time.
Yes, that's real time, and it's used already by other NEPTUNE centers.
Okay.
Yeah. But that one is just the snow cover, and first need to convert into the snow depths. Yeah. But maybe it's like some lag, because that is daily data. But we can if we want to use them, and we can to assign some large arrows.
Deaggregate it somehow.
But it's too valuable for the 0 snow depths. This one, because there is a snow cover and the 0 snow depths regions, they provide globally, the 0 snow depths regions. Yeah. That's valuable information for the snow DA.
Sure. Thanks.
Thank you.
Any last questions? I think we have a few minutes at the end of our session here if there are any broader questions overall for the session. Yes, as Sergey was bringing up, it noted to me the difference in some cases of slow comparisons to current systems compared to jumping forward to a big system. And it seems like having some of both of those approaches is helping us move forward. But the error checking and the slow process seems like been worthwhile to catch some of those bugs. But.
I had a question. Slide where
you use the mic, sorry.
Yeah, you showed a slide where you were trying to make up, you said, I think we can save here, I think we can save. I wasn't quick enough to do the arithmetic. Does that get you from 61 to 40 or something yet? Or like, was there hope? You know the one, slide I mean?
Yeah, I didn't do the arithmetic easy if we're going to get to 44. I think the point was that we have places where we can save room, right? But we haven't stress tested it. We'll have very few offs. So I think once we actually add aircraft, satellite wind, hyperspectrals, then we might find completely different bottlenecks that we haven't seen yet.
All right, I'm not aware of any other general announcements. I think it's on to lunch break and reconvene at 1:20, I believe. Thank you, everyone.
So welcome to the composition application section. So we'll have 4 talks. So first one will be given by Jérôme Barré on the JEDI composition project progress and status and plan.
Thanks, Sarah. Hope everyone has an happy digestion. So I'll present the plan for the atmospheric composition project at JCSDA. I won't talk so much about results. There's a talk from Maryam about really specific results and what we've been doing with SKYLAB. So I will take here in this talk the opportunity, since the atmospheric composition project is fairly new, it's a year and a half now since I started, more about like what we are envisioning for the atmospheric composition to be developed over the years at JCSDA in terms of capability. And what are the area of focus? So we define like 4 areas of focus. I call it the palette because it's related to composition. When you paint something and you think about the composition, you set up the color of the palette. So I think the first element in the palette is like what I would call the NWP sensitive data assimilation. In NWP, I talk about meteorology for people that don't know the acronym, numerical weather prediction. So this includes aerosol, stratospheric ozone, and other sensitive gas down the line. And this also includes like level 1 data assimilation. I think there needs to be an effort to put atmospheric composition on the same plane as the rest of the atmosphere. The other element is like the emission and fluxes. So we need to extend the data assimilation capability for fluxes and emission constraints. And here there's a clear like focus on anthropogenic emissions, but not only, also on fires and also vegetation fluxes. If you start to think about carbon cycle, this is crucial. And you can also think about like chemical reactions being flux as well. And the last but not least is the air quality and going across the scales. So we need here at JCSDA to facilitate high resolution data integration with a particular focus on geosensor. So there's we know about the recent launch of Tempo. More early there was a launch of GEMS, and there will be over Europe the launch of S4, and those will be sensors that will look at the polluted area of the world, the 3 main polluted area of the world, and it will be crucial to integrate this correctly at JCSDA. This goes with like the focus on novel geometries, high resolution, and stretch and refine grids. And obviously, when you think about air quality, you need to think about also integrating surface observations. Those are a main driver for constraining the state for air quality as well. Okay, so to go more on the specific of the focus and what we are working on and what we are working on, one big things toward joint NWP and aerosol DA is the aerosol assimilation problem. So in the state, in aerosol, there's many variables, and this causes a problem to do this jointly with the NWP data assimilation. So we need to reduce the control space to increase analysis resolution. So, you know, if you look at like the plots over here, you look at the dustbins, you know, the 5 dustbins in go-kart, And you can see obviously like very strong correlation between those variables. So you can use actually localization within var or a balance operator to account for those correlations. Just to clarify here, there's two ways of assimilating aerosol in JEDI. The first way is the calculation of extinction profile at a given wavelength from the model. And basically, a UFO, the observation operator, sum over vertical and provide a AOD at a given wavelength. So the advantage of this is you have only one control variable per wavelength. This is cheaper, so that allows you to run analysis at higher resolution. But this also exacerbates errors in the prior. I won't go into the details, but because you don't have like all the variables represented in your minimization, you have this kind of problem. The second way is the calculation of AOD. Directly from concentration. So you use a CRTM or a lookup table loader to provide AOD at a given wavelength. And here the problem is that the control space is the size of the state. It is way too large. So it's expensive and you cannot run a high resolution. Though the idea here is to try to find a middle way and how to account for those correlations. So the other important topic here is like the level 1 assimilation. I like this figure. It's not very accurate, but it looks nice. So it's just to give you like where are the things that are relatively sensitive in atmospheric composition, and I think one big part is the visible part, and this is very fortunate that like CRTM is developing new capabilities for visible. So I think in the first stage we will look at aerosol sensitive assimilation in a radiance, and later on we will look at trace gas. But there's one challenge about the spectral resolution and the cost of this. So that's not really like immediate priority, but that's still important to keep in mind. And I also invite you to like keep a focus on like what Shih-Wei will present in this session, which is like aerosol-aware infrared sensitive DA. So it shows that you will see, it shows that you have like impact from aerosol in radiance assimilation. Okay. So the second step to be more specific, why do we do emission and fluxes, and why do we want to do that for atmospheric composition? So you need, and there's a dear need in data simulation to develop an emission monitoring verification support. So you need to be able to inform the policymakers about like what is being emitted and where and what. You have emission inventory, but they lack timeliness. Things are reported way too late before things happen. So you need to develop a data simulation system that can give you an answer on emissions. So for this, you need to develop a 4D VAR. This is not necessary, but this is the optimal way. And we plan to use a hybrid TLM to add like chemistry and physics. Machine learning surrogates should also considered, but this is not necessarily very but should be very interesting. So we need to develop the interface and the workflow to handle emissions, post and pre-processing in JEDI. And the idea is to how you project the increment over time, over the windows, and also how you infer like the sectors in emissions. So just to explain why we need like a 4D VAR formulation for that, why this is the ideal, is because when you have like a satellite observation that is far from the source, you want to be able to go back to it within the inner loop to produce an increment where you have those emissions. If the assimilation window is short, you have a problem. You won't be able to have the sensitivity to the emissions. Then you can think about like if you have a new sensors, you increase the sampling of satellite observations. So the short association window is less of a problem. And you could consider things with ensemble, for example, extending the localization range and localization observation space, and how you could infer that. But that means you have like enough sampling. With the requirement for increased resolution, this is not necessarily in a state. This is not necessarily a given. So that's why we still need to have 4D VAR, but the ensemble information will be very necessary as well. Okay. I think there's a battery problem. Oh. Okay. No. Almost. Oh. Jesus. All right. Okay. So it's just like just a satellite plot that I did like years ago, but still very good to illustrate like the problem of co-emission. It's not because you have like one chemical species and another that like things are not linked, you know. And you can see that really like in satellite observation, things are co-emitted. If you look at the enhancement, the high values, you can see similar patterns. They're not exactly the same, but they are quite similar. That means like things are co-emitted. So you can use like assimilation of an observation, for example, of NO2 to potentially constrain something else, like for example CO2, which is very hard to observe in the atmosphere. So okay, to on the last, how am I doing on time, Sarah? Did I speed up? Still good? Okay. So on the last theme of the composition project is like the air quality and scales. So what we need in terms of background and modeling capability is something with a refinement or higher resolution. We can have for the air quality scale, meaning we need something around the kilometric scale or 4 kilometer to run chemistry 4 kilometer globally. This is really like still not possible. So you need to think about solutions. So one first solution that's already exists and is tested and implemented at NCEP is to use a nested domain within the FV3 geometry, and then they use a CMAC. The problem is that with nested domain, they require an extra effort for OPS filtering, for example, and lateral boundary condition. Right now, if you're interested in long-range transport, which is important for air quality, the current system with CMAC won't be able to represent this unless you have like very good observation close to the boundary condition in the influx. So one solution to move and to palliate on this, not necessarily palliate, more like improve this, is to look at FV2 stretch grid. So right now we are about to run with GCHP a stretch grid, and we'll do the testing very soon to make sure like the interpolation works and we can run HFX on stretch grid. The other alternative is to look at MPAS and the refined grid. And here, I think we're really hoping to have like chemistry or also scheme available to start to test this with JEDI. Did I miss something? I thought I had more slides on air quality, but I think I don't. Yeah, one slide is missing. Like something. Okay, one slide is missing. I will talk without the slide about like a tempo and geostationary instrument. So basically, we will work on tempo very soon. Tempo has been launched like a month and a half ago now, and we will have data release probably in the fall. And we really want to be on top of that at JCSDA and start to make first monitoring demonstration with the refined grid. And this is very important to consider with like the geostationary constellation that I talked about earlier in the introduction. So we need to have high resolution background to ingest those high resolution observation and hopefully try to start producing analysis as well. So, you know, what we can have down the line with this palette is like mixing the colors, right? So one thing in the interface of those teams will be like using an NWP assimilation configuration is probably the best way to represent transport errors, right? And for emission fluxes, like the transport errors are crucial. If you don't represent those errors, you are not doing, you won't be doing a good job. If we think about like emissions, you can think about carbon cycle. So if we want to do a CO2 emission monitoring, we need to have carbon cycle. That won't be possible otherwise. So this is air system data simulation effort. We need to have engagement for the carbon cycle community at some point at JCSDA. So if you want to think about developing a capability for human emission monitoring verification system, you need the input from the air quality systems in order to report useful information to policymakers. And this goes with the topic of co-emissions. I mentioned NO2, for example, for traffic. NO2 is a very good source of information to infer on CO2 concentration. So you need to link those compartments with between each other, climate and air quality. And conversely, I think air quality will really benefit from surface flux constraint at the surface. That would really improve the skill scores over the forecast, because you will constrain the boundary condition. Like the atmospheric chemistry is as much a problem of initial condition and boundary condition as well. So at JCSDA, we're talking about like data simulation in convective scales. And I think this is really improved to move toward those scales for air quality as well. So there's an interaction between NWP activities and air quality activities here. And finally, if I can do it, I think it's out of battery. Oh, yeah, quite a bit. Anyways. Let's move forward because so in terms of like SKYLAB, I think I would refer to like Maryam's talks in a matter of time. But this is what we have done over the last year and a half, and we've put the building blocks to move toward those themes I mentioned. So in terms of target configuration, in 2023 we'll have hopefully a cycled EDA of 3D VAR for Aerosol. We hope to have a cycled 3D FDR for trace gas with GeoCF, and we'll plan to do a demonstration of 3D HFX for a tempo with a refined grid, with a straight grid. And the year after, I think we hope to increase the resolution for Aerosol and maybe start to integrating level 1 assimilation. And I think we can try to have also like a hybrid TLM with a cycle of 40 VAR in 2024. And that will be like, if we achieve that, that will be the time to move towards GHG, because we will start to be attractive towards the greenhouse gases community with that capability. For refined grid DA, I'm seeing like, I think a good way to treat air quality is to move toward 3D and VAR using geosatellites. Yeah, that has been, that's it. I don't know what happened to the slides, but I talked about that already, so. Okay, in terms of evaluation and quality control, I think quickly we're trying to have a simplified and generic Atlas interface. So basically Atlas allows you to handle like multiple geometries. That doesn't mean there will be like an interface that does as much as FV2 or MPAS, but that will allow you to do a HFX 3D and maybe down the line to produce an increment. I think this is very important for what was mentioned at the beginning of this meeting actually. How can we have more outreach towards the academic community? So having simpler interface like this, I think it's will be very attractive towards not just the operational world, but the academic world. And I invite you like for more evaluation, quality control things. I think Sarah Poster, I think we'll talk more about this. Okay, just to conclude, just a brief reminder. So if you ask Google, what is the yearly estimate of cost of weather in the US? Google says climate and weather disaster cost $165 billion a year. If you ask Google the question, what is the cost of air pollution in the US? Google says air pollution from fossil fuels costs $820 billion a year. Okay, so I think we should, try to invest more for data simulation in general, for air quality, and what we're trying to make sure we can control what we are breathing. And I did like the more modern way. And ChatGPT confirms. So yeah, thanks for your attention. I will stop here.
So we probably time for one quick question from the audience. Okay. Thanks. Okay.
Yep.
Weather versus composition stuff. And the costs are very high for a chemical DA, especially when you involve like these long time windows for emissions.
Yep.
Are you coming up with configurations with weather DA people where you can kind of come to a middle ground, or maybe your past experience at other organizations has enlightened you in some way? Are you bringing anything in there that means this is going to work, that gives you hope?
So I think you should think you cannot have a single configuration, because if you think about like for the emission reporting, the time constraint is different from like, for example, similar than air quality, which is similar to NWP, where you have to deliver an analysis and a forecast every 12 hours, every 6 hours. For emission, you would need to report something every month or even less. So the time constraints are really different. So the way you would implement the system is also very different. So, you know, for the window extension, I think you could do it, but they won't try to fit what NWP is doing. You would need to have the input from NWP for the transport error. So you need to think about a system that use what NWP is giving you, right? I don't have the answer, the implementation answer, but basically that's what you would need to have. Thanks.
Okay, so the next talk is on the development of JEDI-based aerosol assimilation system for global aerosol forecast at NOAA, and will be presented by Mariusz Pagowski. I think it's online.
Good afternoon. Do you hear me?
Yes.
Okay. First, I'd like to acknowledge the collaborators and contributors to this work across NOAA, NASA, and JCSDA. So we configured and we use JEDI-based data assimilation system for near real-time aerosol forecasting. And we also had a pilot project at NOAA to produce global aerosol reanalysis for year 2016. And now we continue for the following years. And slide 2. So this is the outline of my presentation. I will first talk about the near real-time system, then about the global reanalysis, and in the end about problems that we see for DA for our application for aerosols, and that we face, and we want to address that in collaboration with the JEDI team. So slide 3. So to give you some background, what Jérôme said about this multiple beams of species that cause really big burden for data assimilation, and that between beams of dust and sea salt that correlate highly, it will be something to really convince the modeling community very much, not only data assimilation. But anyway, in near real time, we have we're running this system using NOAA operational model that is called GEFS aerosols. A little bit earlier version, not entirely up to date. NOAA started developing an upgrade to this model that is called UFS aerosols. And this new model is even closer to NASA's GEOS, with some NOAA's modification to dust uptake and to wildfire emissions. But all these models have very skeletal chemistry, but are more extensive in terms of physical parameterizations. So that in addition includes in addition to transport and mixing, include emission uptake, dry deposition, and grid and subgrid scale washout. So the parameterization is called GOCART. The current one has 18 aerosol species like dust, sea salt, smoke, organic aerosol, sulfate, and nitrate. And we have data assimilation system at NOAA that we configured also for this newer model, and we're ready to deploy it in near real time so we can compare how much progress NOAA is making with this model upgrade. We assimilate aerosol optical depths, which is an integral of light extinction by aerosol column. And in our case, we assimilate AOD at 5 50 nanometers, which lies in the green part of the visible spectrum. And our retrievals come from VIIRS instrument on polar orbiting satellite that's called Suomi NPP, and they are obtained at NESDIS. So slide 4. This is our configuration of the system that is based on JEDI in its entirety, almost, I think, except for data thinning and formatting. And it has 20-member ensembles, 20-member ensemble, and is a standard 3D NVAR configuration. The model has 64 vertical levels and about 100 kilometer resolution. And because our ensemble spread was deficient, and is still deficient, but we implemented, to improve on that, we implemented inline perturbation to emissions in the older model. And these perturbations rely on stochastic scheme that was developed at ECMWF and is also employed in GDAS at NOAA. Slide 5. This is what we display on our, this is what we display on our website in real time. So we verify against independent observations, and this includes ground-based retrievals, very high quality retrievals from Aeronet stations, and we also have a comparison with retrievals from MODIS at NASA, retrievals that are developed at MODIS, from MODIS at NASA, and we also compare to the analysis to NASA and ECMWF, and we update that daily and display on our website. And slide 6. So this is illustration of some problems that we face in terms of how much we can improve the data assimilation. So in the first column, you can see VIIRS retrievals plotted against the Aeronet, which we consider ground truth. And you see that the correlation is not that high, really, and there is some bias. This kind of creates a limit, really, how much skill our analysis can have. But aside of that, you can see that if we compare free model run with the analysis, there is a marked improvement in all these essential statistics. So let's go to the slide 7. And that is comparison with ECMWF at NASA. And so obviously, because models are so much closer between NASA and NOAA, we have better statistics against NASA. But the other point is that even in this coarse kind of observations that AOD is, there is significant or marked differences between ECMWF and NASA. So there is no really something, objectively that can be trusted entirely, even in terms of AOD. Not talking about the species that I will go later to. So slide 8. So this is another part of my talk that I will devote to the reanalysis. So this was a project that we had that actually started this whole thing at NOAA. Started in 2018 and concluded in 2022, and it was actually in collaboration with NASA, which provided observations, and SUNY. So it was a pilot project just to develop global aerosol reanalysis for year 2016. This was the first reanalysis at NOAA. We called it NARA short for NOAA aerosol reanalysis, and we produced it, and we have some critical discovered problems, obviously, with it that I will talk about a little bit later. And we have it, can be downloaded. So we assimilate neural network retrievals that come from GMAO, and this is in contrast to what we assimilate in near real time, which is VIRS. So we can look at the statistics against AeroNet. So it's a significant improvement. Bias is reduced and correlations are on average 0.2. So that is improved, is significant. And also you can see how it compares with MERA and with CAMS array. So obviously, as before, much closer to MERA2 than to CAMS array for reasons that I talked about.
Size now.
Okay, should I repeat what I said or
No, continue, sorry.
Anyway, that's that, and NASA and ECMWF's CAMS array. So we can go to the next slide. And that is more strict evaluation because we pay more attention to the individual aerosol species. And I picked two domains here, which is this subtropical or tropical domain, just through Africa and the coast, and Russian domain and also Siberian domain, because this is where there is significant mixing of two species of dust and of carbonaceous species that come from wildfires. And for that reason, the analysts have a problem with it because they don't know how to apportion the species. So, for example, MERA gives much higher ratio to dust than the CAMS array, for example. So this just is an indication how uncertain the aerosol concentrations or mixing air ratios are, and also limitation points to the limitation that assimilation of AOD creates, because it's an integral, and it's integral to the column and it's integral to the species. So it creates lots of the assimilation of such quantity is a poor constraint on individual aerosols. So we can go to the next slide, which is will lead us to the challenges that we want to resolve with next, and we'd like to do that in collaboration with the JEDI team. So this is slide 12, please. So first thing we want to do is to, as you can see, AOD is not Gaussian. The errors are not Gaussian, and we want to correct that by transforming into the log space, which is much better reflected, much better approximates the errors. So that should be, we think that would be a relatively easy task. Well, that looks very good in theory. We'll see how it works in practice, but it looks promising because the fits are quite good to the log normal distributions. Next, we want to, because, no, next slide. Sorry, can you go back? Yes, so the bottom is about, because we have the pixels, AOD pixels at 750 meter resolution, which obviously cannot be assimilated. And we want to, and we have the ground truth from AeroNet, so we want to derive errors and aggregate observations also. and use this super ops in the assimilation. So the next slide, please. And that is a little bit more difficult task, which is to, because our ensemble is under dispersed, we need to improve the spread. So we would like to have similar methodology that we applied for the GEFS model transfer to the UFS model, UFS aerosols model, but we want to explore more perturbations that would impact the spread in a more comprehensive manner. And finally, as you can see, maybe not finally, but we need to address model biases because it's not as much observation biases, but how model biases, how large they are. So that requires a comprehensive approach. I think we have an idea how to do that, but it needs collaboration with you and some more experimentation. So the next slide. And this is to stress the deficiencies of the model. So here, or deficiencies of the model and also limitations of AOD. So that is basically to show that you can, we assimilate the single AOD and has little impact on the species and on the relative contribution of species and also on sizes. And this is manifested in angstrom exponent, because angstrom exponent compares how different aerosols, how they absorb in different parts of the spectrum. So each aerosol has this specific absorption spectrum and scattering spectrum. So if you assimilate AOD at different wavelengths, you can get some insight on some correction to this to the composition and to the beam sizes. But as you can see, this AOD, this angstrom exponent changes very little with the assimilation or without the assimilation. So that's something that needs to be corrected, and we hope that these new missions like PACE that will be launched shortly will provide the new retrievals that will help to address this problem. And finally, there is one last slide with the. Can you go to the next slide? Yes, that is this healthy issue that is very important, because aerosols are very harmful with this some that Jérôme mentioned, and one of those really that are of primary importance are small aerosols. Are called PM 2.5, and they are the models in general poorly predict this concentration. So that's something that should be really paid much attention in the future. And so as you can see, the scatter somewhat improves when we assimilate AOD, but is still very large scatter and very poor skill. It's 100-kilometer resolution, and PM can vary spatially very significantly and temporally as well. But still, we would like to get something better. And the other issue is whether AOD how much it can improve PM 2.5. AOD is this common observation, most common satellite observation, but it not necessarily can correlate well with surface concentration, because there may be multiple layers of aerosols in higher elevations and so on. So I just that's the final slide. I just want to acknowledge the grants that we received and all the contributors that we had to this work, and thank you for your attention.
Thanks. So we have time for a quick question from the audience.
Hi, Mariusz. This is Ricardo. What's the resolution of the NCAF stuff that you're doing with JEDI now?
So we have the same resolution for the VAR and for the NCAF. So that's 20 members with 100 kilometers and 64 levels. But we are migrating to C192, which is 50 kilometer, 127 levels. But that is still a lot coarser than you are running, of course.
Thanks. So the next talk will be presentation by Mariusz, and she's going to present a data assimilation atmosphere composition using JEDI-SKYLAB.
Okay, can you hear me? Hello, everyone. My name is Maryam. I'm a computational scientist at JCSDA, and I recently started working full-time in the Campo team in February, and before that, I was on the infra team for the JEDI project. So before I start, I want to thank all the co-workers in different agencies and also the JCSDA core staff. So let's start with JEDI. You know what that is. So you probably know. So JEDI is as you know, it's a unified data assimilation framework for Earth system prediction. And the development of JEDI, it's done through collaboration between different agencies, as you know. And one of the great features it's one of its great features. So we have more than 100 developers on the team working on this project. And one of the important things that makes the development efficient and possible between these 100 developers is the kind of agile methodology that we use in our development. So that means that we have lots of smaller tests that we run when we want to add a new feature to the system. And also larger tests that we use to kind of an application type of test that we use to kind of test the whole DA framework, which today I'm going to talk about that application test that we have and show you some results from the perspective of composition and all the development that we've been doing in the past year, I'd say. So in a data assimilation system, you have multiple steps and the workflow is kind of complicated. So you kind of start with ingesting observation into your system, bringing the backgrounds from your model, and then also combine those using your data assimilation algorithm, produce results and also generate plots and evaluate your answers. So this, for us, we kind of put this whole process under the label of JEDI-SKYLAB, which is the end-to-end data assimilation system of JCSDA. And today I'm gonna kind of show how we set the SKYLAB experiments for the aerosol and also trace gases using different models and different observations that we ingest into the system. And also all the plots that I'm going to show today is coming from SKYLAB. So it kind of shows all the capability that the system has, and also how it's kind of easy to add new features to this SKYLAB kind of workflow, because it's all written in a very generic sense. So it's pretty flexible and versatile to add new observations or add a new kind of DA method, or kind of play around and kind of change the workflow in a way that you want for your DA application. So I'm going to start by focusing on aerosol. And then, so I'm going to call these experiments Skylab Aero experiments that is based on GFS Go-Kart. And as I mentioned, when we started adding these into Skylab, we started first by ingesting the observation and creating the obs operator or H of X. So that was our kind of one of our deliverables for one of the kind of Skylab releases. So for this, I'm showing the observations from 4 instruments that four types of observation that we ingested into the system. So it's VIRS, 2 VIRS and 2 MODIS observations. So for the backgrounds, we use GFS Aero with C96 resolution, and we have this golden month, which is August 21, and we run most of our experiments for this period. So this was very interesting to see, to kind of add that into that kind of Skylab framework. So this H of X feature can be used mostly for monitoring purposes, but it's also a good starting point to add a more complicated DA kind of workflow into that. It was a great starting point. So for the next deliverable, we focused we tried to run a 3D VAR experiment. So we focus on kind of developing and training our static B matrix. So we use ensembles that was provided to us by NOAA, and then using those ensembles, we trained our static B matrix for a month. And that is kind of the blue B in the equation on the top. And then with that, we could now run 3D VAR experiment easily because we already ingested all the observations and we have our obs operator in the system. So here I'm showing on the right, it's the obs value. And then in the bottom, you can see just a sample of increments for sulfate and sea salts. And you can see that the spatial distribution of sulfate it makes sense. So it's over the more polluted area, and also for sea salt, you can see that over the ocean. And so looking more into the results, so we ran one experiment where we assimilated VIRS NPP. And here I'm showing on the left, it's the plot from observation minus background. And on the right is observation minus analysis. So basically comparing these two together, you can see how much your model fields or your model state was improved after doing data assimilation. And looking at the mean and standard deviation, you can see some improvement that was done. So you can, in this experiment, we just use VIRS MPP for assimilating and also VIRS N20 for monitoring. So you have the option to add to the YAML that you just want this observation to be in a monitoring mode, and then you can just look at the results there, and it will not be calculated into the DA cost function. So because we improved the aerosol fields in the model, we also can see that in other independent observations as well. So here I'm showing results, the same type of plots for VIRS N20, but showing improvement again when you're comparing left to right, seeing improvement in aerosol fields, looking at an independent observation. So now I'm gonna switch to trace gases, and this type of experiment we call the Skylab trace gas, and it's based on GEOS CF model. Similar to the aerosol experiments, we start by ingesting observation, developing our obs operator to have the model fields and start comparing them in the first stage. So the backgrounds was provided by our NASA collaborators on this, and we are using GeoCF in C90 resolution and for the golden month, which is August 21. So we have tropomi NO2, both total and tropospheric column, and also tropomi CO and MOPID CO in our current Skylab trace gas experiment. And then again, building on top of that, we calculated static B values, and then using Sabre and Bump, and expanded on the previous work and ran a 3D VAR experiment using all the observations and also using GeoCF background values. And here I'm showing some increments for CO on the left and NO2 on the right. So again, we ran a similar kind of test that we did for aerosol, where we assimilated tropomi CO and used MOPID CO as monitoring. And we see similar results, improvement when we do DA, when we look at tropomi CO, and also, of course, because we are improving CO in the model, we are also seeing it on independent observations as well. We also assimilated NO2 as in this 3D VAR experiment. But for NO2, we are not seeing a strong signal or strong improvement when we do data assimilation. And that's one of the main reasons, is that our model resolution is too coarse for that. And NO2 is a short-lived species, which is very localized. The pollution for NO2 is very localized. So you really need higher resolution model in order to capture NO2 and use DA to improve your prediction. And also, we're going to test with using smaller correlation length scale in our static V to see if we can see any improvement there. But mostly, we need to focus and go towards higher resolution backgrounds and modeling. So this is a summary and future work. As I mentioned, one of the nice features of working with JEDI, which was very kind of exciting to me, is that you have all these building blocks and you can use them to kind of build the system, the DA system that you want. So you don't need to make all the changes all at once and break the code. You can just add them stage by stage. And this goes really nicely with the quarterly releases that we have. So we have this goal for each quarter, and then we work towards that. And then we can kind of make the system more complicated as we go forward. So some of the other achievements that we had in the past year was that right now for composition, we have model interfaces between JEDI and GFS Aerosol, GEOS, GeoCF, and also GCHP. And Jérôme mentioned that with GCHP, we are going to explore high resolution model and also stretch grading with that, which is going to be very helpful for kind of looking into more reactive species. So for static V, as I mentioned, we use Bump and Sabre to train our static V for both aerosol and trace gases. And in order to ingest all the observations that I mentioned in the talk, we developed all these Yoda converters. So for VIRS, MODIS, tropomi NO2, tropomi CO, and also tropes CO. So we have all these converters in the repository now. So anyone can use them to kind of convert the ops data into Yoda data or the JEDI formats. And then in Yoda, we made some changes that now we can handle 2D fields in the ops files or in any Yoda format, which is an improvement in terms of code performance and also the way the kind of the files were compared to before. And then some of the few things for the future work. So the 3D VAR that we run and the experiment that I showed you, they were all non-cycling 3D VAR, meaning that we only calculate analysis and we don't really move the model forward using those in starting from those analyses. So we need to really focus on that. So the result could make after that, it would scientifically make more sense and we can do like lots of cool science with that. So for me, I'm going to focus on GeoCF, but in the group, we're also going to focus on UFS aerosol or atmosphere aerosol and run the cycling 3D bar, which is going to be very exciting. So Jérôme also mentioned tropomi data. That is also very exciting. We're going to have high resolution observation, and we want to make sure that JEDI is ready for that. So that means that we need to also focus on high resolution model, stretch gridding, or anything else that can get us to that higher resolution that we need. And after that, we can then focus on source inversion and improving emission estimates. So this is my last slide. Thank you.
So we have time for a couple of questions from the audience.
I guess I could ask this also from the earlier speakers, but has there been any thought about bias correction for this type of data? At GMAO, probably we use a neural network to debias the data that the AOD information. So I don't know if there is, and we do this beforehand, so we don't do an online bias correction, such as RBC. So is there any thought of doing either that or something else, or what are the thoughts?
Yes. So there are plans to do that. So I just included some of the future work, but that's in the AOP to focus on that as well.
We have time for more questions.
For bias correction, for aerosol, for IoT, I think using new product is a very good way to evaluate and benchmark the variation of bias correction with the neural network. So I think that would be very helpful to have it and ingest it and making sure we can use it and put it in the system. And then, probably a very good way to evaluate bias correction, variation of bias.
Right, so I guess we can move on. Thanks. And the last talk, but not least, will be by Shih-Wei Wei, and he's going to present the Aerosol-aware thermal infrared radiance data simulation.
It's just okay. Hi, good afternoon, everyone. Let me just add one more thing. One more thing, application for aerosol and the interaction with the aerosol and the NWP is not normally less people focus on this one. So it's partially my PhD work. So I just finished it by last month. So right now I finally finished graduate. So yeah, so it's the topic is actually about aerosol-aware thermal infrared radiance data simulation. So it's a little bit different to the JEDI frameworks, right? Everything you these 2 days you hear. So it's based on the global GDS system, which is based on the GSI. So let's go on. So we already a lot of study already try to access the aerosol impact through the physical the ray effect and indirect effect through for the radiation budget and also the precipitation stuff. So there are many this kind of study working on this, but we also several papers already also mentioned the aerosol can reduce the brine temperature within the thermal infrared window regions. So and there are a couple of studies also mentioned about if we consider this kind of aerosol attenuation, the absorption and the scattering within the retrieval or the radiance observation operator, it can produce a warmer analyze the temperature at the surface and the lower level atmosphere, or especially over the aerosol laden region, like the transatlantic region with the dust plume. Yeah. But right now, in most DA systems, we don't for the infrared data, we most likely to just only assimilate the clear sky data. Like for ECNWF, they actually implement one QC check to remove those data considered as aerosol affected. But through that QC flag, we can see the right, bottom right panel, the figure from the Gear et al. 2019, it shows over 60% data during 1 week over those dust aerosol laden region will be identified as aerosol affected and then reject. So in this work, I actually consider if we can assimilate those 60% data during those aerosol laden region, can we have analysis and forecast down the road? So in this talk, I will introduce one Aerosol-aware framework to try to assimilate those hazy sky data. So in this Aerosol-aware framework, it's basically similar to the all-sky framework for the cloudy sky data assimilation. But for the first thing we need to do is identify which data is aerosol affected. So I implement the cloud aerosol detections package from software from the EUMETSAT. They developed the software to identify aerosol affected data based on the multi-channel brightness temperature differences. So with that capability, I can see which I can get a data set which is aerosol affected, and then I incorporate for those hazy sky data, I incorporate the model's 3D aerosol mixing ratios, which can be from the GOCAR model or mirror-to analysis data. And with that aerosol information, we can provide to the CRTN as a first case state, background stage to consider the ambient condition and the aerosol information and generate aerosol affected brightness temperature. And then based on the aerosol affected brightness temperature, we can calculate the aerosol effect parameter, which is also a similar thing, also adapted from the Okamoto's approach. In their study, they introduced cloud effect parameter as a proxy to quantify how much to quantify the cloud effect on certain observation point. So here I use a similar way to quantify the aerosol effect on observation points. And then based on the aerosol effect parameter, we also adapt a similar way to assign the observation error when there is a larger aerosol effect on certain data points. But one thing I need to mention is because current in this framework, the aerosol detection method still have some limitation. So with the confidence of accuracy is much less than we don't have very high confidence about the aerosol detection. So we keep the cloud QC in GSI to screen out those possibly affected by cloud and aerosol together at the same time as those observation points. So here is the aerosol-aware QC flow within the GSI I introduced. So one thing I would like to point out is originally in the GSI we only run CRTN once, but right now because I need to use the cloud QC for hazy sky data as well. So I run CRTN twice. One is for the cloud QC without any aerosol information. Another one is the hazy sky, the aerosol affected brightness temperature with the aerosol information from mirror-to. So after that, I also introduced some bus QC to try to screen out some extreme condition for detected by the aerosol detection method. So in this presentation, I conduct a GDS experiment for the period from June 1st to July 10th, 2020, because in this period, if you remember, there's one big gases are dust plume transported crossing the Atlantic Ocean and affect the U.S. So during this period, I conduct 2 experiments. The first one is a clear sky framework, which is just the original default configuration. And then the second one is the aerosol-aware framework based on the aerosol-aware QC I just mentioned. And then I incorporate the mirror to aerosol mixing ratio, which is, I think, at the current stages, we can have a base estimation of aerosol fields right now. So we use this one as a part of a background state to generate the aerosol affected brine temperature. And then in this study, I only use this aerosol-aware framework on the gases measurements, and because some issue because we haven't touched anything with bias correction yet, so we exclude those hazy sky data from the bias estimation. And within this part, I actually use the CRT and version 2.4 with the default lookup table mentioned by Chen yesterday. But the reason I use version 2.4 is because in earlier version, we actually, after we consider the scattering process in the radiative transfer model, CRTN has a bulk layer. It will have a negative sensitivity of the surface emissivity. So it actually will have it actually is a wrong impact on the bias correction if we put that kind of information into the original GSI system. So I need to use CRTN version 2.4 for better, I think, better results. Yeah. So another reason I selected this period is because in my previous study, I also noticed that dust aerosol actually can generate the strongest cooling effect on the brine temperature within the infrared window region. So that's actually because dust aerosols have a relative similar effective radius as infrared window region wavelength. So it can scattering and absorb the thermal infrared radiance during the window region. So here is one result about my QC of a window channel from the 2 experiments, the QC results. So I think it's really hard to see, but within the circle, red circle is actually the dust plume. The dust plume just operates through around the Africa coast, and then in left-hand side, the control run. The control run is the blue dots actually means originally in GSI system, it considered this as a cloudy sky. So those data said originally be rejected by the cloud QC. Very well, we don't have this kind of misinformation be assimilated into the system. So, but in the aerosol run, it originally, those data points be identified as hazy sky data. And, but because we have less confidence to the aerosol detection method, so we keep the cloud QC for those data points. So, in the end, those data are still rejected by the cloud QC. But if you can notice, there's some data points is pink colors. Very few of them. Those pink colors data points are aerosol affected data and assimilated within the aerosol-aware framework. So in the end, only very few, about 4 to 6% data within the window channel are aerosol affected. But given this kind of very small, tiny amount aerosol affected data, we still can see some impacts on first impact on the first gas departure for the brine temperature within those brine temperature first gas departure within the window channel. So the triangle, the red triangle is the aerosol run. So you can see the mean first gas departure in the aerosol run is slightly more positive than the control run. And based on based on this warmer and more positive brightness temperature first gate departure, it actually creates the generate a warmer analyzed sea surface temperature, especially during the Gaussian dust plume outbreak period, like I point out that during the 23rd to 28th period, and then with the aerosol-aware framework, we actually can reduce the SST bias over this period, and then also reduce the Loomis square first gate departure. And most likely, from the 2D distribution, you can see the Loomis square error is improved over the transatlantic region. So here I show some statistics comparison with the ER5 reanalysis. Here is the global average, so you barely can not see too much impact. Most likely they are it's a neutral result, but the thing I would like to point out is like for the middle upper panel, you can see the black dot line, solid line, black solid line, which is the bias differences between the two experiments. So the positive value means we have a warmer lower atmosphere. And another thing I would like to point out is for the U wind over the 600 millibars. You can see we have a more westward zonal wind compared to the control run, and this signature is basically most likely contributed by the tropical region. Here is the transatlantic region statistics. So you can see the U winds still have a more westward zonal wind, more westward U winds, and also it has a better agreement with the ER5 reanalysis. And this kind of flow change we can consider it will affect the African easterly waves behavior in the forecast stage. But given the small impact, probably won't change too much, but we can expect that will have some impact on the circulation. So here is the anatomic correlation coefficient from the 7-day forecast based on their own experience on analysis. So basically, you can see there's no significant difference and between these two experiments. So basically, the 7-day forecast shows neutral results. But if we focus on the verification with against the observation, you can see there's more blue color in a global scale. You can, some blue color over those area with larger Loomis square, or like for geopotential high, you can see over like 5 and 6 days, you can see some blue color, and then also the temperature also have that kind of the features. But if I focus on a tropical region, it doesn't show too much difference between the two control runs. One reason maybe is due to the observation is probably much less than the in a global scale, and another thing is probably those observation probably most likely over the land, only majorly over the land. So, but the impact from my experience most likely concentrate on the ocean region. So here's the conclusion. So basically, this aerosol-aware framework, we can consider some aerosol information with about only 4 to 6% of those aerosol assimilated data. But encouragingly, it shows better agreement with the sea surface temperature, and there's no too much degradation, or it shows a neutral result against the ER5 analysis and also the anomaly correlation scores. But like I mentioned, there's a large portion of hazy sky data was rejected. So due to we would like to constrain those uncertainties from the aerosol detection method. So this part is one major future work we would like to pursue in the future. So the first thing, just like I just mentioned, because I didn't mention what's the limitation within the current aerosol detection method, because in that method is basically depends on the data set we are using right now. We use the NCEP pre-buffer data. So the channel available within the current pre-buffer data set is not, it's only have like a 1 or 2 channel available for the key channels used to identify the aerosol detection method. So you will have a larger uncertainty when we use those. Probably we will introduce some noise within the aerosol detection method. So you will have a larger uncertainty. So the first step is probably we would like to work with full spectrum data, which is also the original data set used in their aerosol detection software provided by UMSA. And then the last thing is I also would like to pursue to migrate this work to JEDI. Yeah. So the first thing is the first thing I would like to want to introduce is the aerosol detection for the hyperspectral infrared data sensors. And then the second part is develop the bias correction for the hazy sky data. So thank you all.
So we have time for a couple of questions.
Oh, the AE calculation.
Huh?
The AE, yeah, the
Aerosol, you mean AE? Oh.
Right. So I didn't quite understand it, or is it something? I mean, this all depends on that. Is this a tunable thing to improve? Oh, you know what I mean? Like you get more data in there, or I just don't.
Yeah.
All how it was calculated, or whether you have any. Sorry. Thank you.
Yeah, I didn't bring this up because too much slides. So
I feel like you have any room, any margin to move this, I guess is my question at all. Weight it or do something to change it, but maybe not. Looking at that, maybe not.
Probably not, but for to include more data, probably we can start from the aerosol detection method first, because it's based on a certain threshold, like the multiple channel. Oh, I didn't show the detail here. So based on the multiple channels. So this is the threshold for the Yardley sensor I use right now, and it's also the same threshold for the aerosol detection software I use from UMSA. So we can change the threshold, but it still have a lot of false alarm. I say false alarm, but because it detects some aerosol. Some data is aerosol affected, but it's not retrieved in the other retrieval product. So I would say that probably is some missing or some error with that. So the better way, I think we should increase the information into the detection method. Yeah.
Any other question for Shih-Wei?
So one more thing I would like to add, yeah, just if you are interested in to push this work forward, please contact Jérôme or Sarah or me or Comforting, yeah, because. Oh.
Shih-Wei, this is Krishna. I've posted a question on the chat.
Sorry.
Oh, hey.
I can read it for you. So it says, very nice talk. Have you performed any impact studies on cyclogenesis within the aerosol. Sorry, I need my glasses on. In the aerosol-aware framework for the Saharan best case.
Oh, you mean like a FSOI stuff? It's not all cyclogenesis. Oh.
Yeah, basically, I mean, you performed the case study, so I was just wondering whether you've performed any, forecast impact for any particular case on the effect of cyclogenesis with and without the aerosol, aware in the aerosol-aware framework. So I was just wondering.
Oh, so we didn't have the study based on the aerosol-aware framework here, but we did some another study based on the previous work, which is no constraint for those hazy sky data. But we do see some impact on the aerosol easterly wave activity, and that's basically that's another study done by Dustin Gordon. Yeah, so we see some impacts, but some positive impacts based on the Roomy square error, and there's some improvement, but not significant.
All right. Okay. I guess let's thank all the speakers before the break.
Okay, so we're going to get started for the next session here. And you're up for a treat. We're going to have the world first live demo of SKYLAB Experiment as a Service. And you're all going to be our guinea pigs because we haven't had a dry run or anything, but I'm sure everything will go super smoothly. So it's going to be a sneak peek on a release of a service we want to release sometime this summer, but we figured we'll give you a sort of a sneak peek. All right, let me get up. With the cookies, I'm just going to fall asleep otherwise. So we've heard, this is just a quick intro and then we'll go to the live. We've heard about a thing I usually don't like to hear much because it's used all over the place, the paradigm shift. But in our case, I think it applies really well. We've really embraced the consortium of jointness. We have actually, a really strong joint collaboration across all these partners here to really share as much as possible, but without actually imposing a single approach and having scientific diversity in all what we do through mutualized tools. Next, please. So there's a lot of work happening. You've seen quite a few examples during the workshop. You'll still see some more in the next day. So there's a lot of deployments of JEDI with different models on different applications, on different platforms, with different configurations, different algorithms, different choice of observation QCs, and so on and so on. So really, how can we actually make sure that we still have enough to actually build these efficient connections? So that graph on the right here is showing that success that we have in jointness right now. When you look at applications, and here are a few examples, we have FV3, so global, this is UFS and GEOS through that global model interface. SOCA for the marine, land is with the Wharf Hydro National Water Model, and then MPAS. If you look how you assemble the code and what's running, actually a lot of the code is generic, reused. So this is all the green and bluish code. The specific code is the red, which is really the model interface. Our goal is actually to keep the specific code as manageable as possible. There's always going to be specificities, so that's totally fine. But whenever you have actually overlap of needs, then a joint solution can have actually a lot of benefits. So next. So what we need in order to keep things really joint is that generic testbed of SKYLAB, the generic testbed of JEDI, and that's called SKYLAB. So you've heard Maryam talk a little bit about it, and so that's what we're actually going to show you today, is how SKYLAB can be a really powerful tool for multiple uses. Next, please. So you can think of it as a concept car that's actually bring together different pieces, and you can actually test it and take it for a test drive and see how these pieces are performing, how you are actually meeting the needs. And that can be a really helpful tool to go to the production car, that operational deployment that various agencies want to do. And you can iterate multiple times and pick what you like, drop what you don't like, and go like this. So it's really about rapid prototyping and validating these developments through that point of convergence, where you don't have to reinvent an entire end-to-end system every time you want to test something. The other thing is, we've talked about agile development, continuous integration. Part of it is making sure that we have a continuously functioning system that can be used, that has basically these latest capabilities that are tested and that can be demonstrated. And once we have something that works, we want it to work in the long run, so that we don't end up in a situation where there was something that worked 6 months ago, but no one's exercised it, and then we don't even know if it works anymore. It might be broken, then you end up actually fixing your own bugs. The other thing, so all of this is really about system hardening, looking at performance, looking at robustness, and skills. So this is very oriented toward research to operations. But there's also the revert direction, the O2R, where basically all these nice features, state-of-the-art capabilities, you also want to actually lower the bar for the communities who have access to it, and not have them have to worry about what data formats the data came in, what kind of data ingest, and what kind of workflow, how do I build the system, where is it going to run, and so forth. So we're providing a turnkey ecosystem for people to start running experiments in that real world configuration, not just a toy model, but actually in that real world configuration, can be really helpful, because now we can actually engage a lot of community members into that development. Next, please. So Mariam showed that slide earlier on, and I'll just explain quickly the part that is very important in our requirements for that experiment as a service, which is basically that generic testbed. We want the different components to be generic reusable, and that is what the Joint Center is about, and that was makes this unique to other applications. Is actually going to be multi-purpose, easily reconfigurable, where you can actually add new data regardless of where it came from, and you go through that YODA API. So basically, we have the JEDI data convention, naming convention. So basically, you don't need to know where the data came from. It's basically populated in YODA format onto our data store that we call R2D2, that has everything on shelves ready to go. Next. Then we want a workflow that can run experiments, fetch all the data necessary for this, can actually grab all the codes and the code for your given configuration. So that means, which components you want to run. Is it the marine, the atmosphere, the composition, and so forth. And what model interface we need. So you need a flexible build system, a flexible workflow that can actually be generic and work on your laptop, on the cloud, on an HPC, that can work with different compiler versions, and that you can really easily repurpose. We also want to go end-to-end and have actually a series of diagnostics that can help you doing science, and then figure out what are the next developments, so that you can go into the agile development and do the next coding. Next. So part of the requirements is actually, we want to make sure that from the get-go, we consider Skylab not just as a specific DA for one component, but really as a sort of integrative Earth system component where you have the various components like atmosphere, the land, the marine, the aerosols, trace gases, all under that one umbrella. You have one data flow, you have one workflow, one suite of diagnostics, one way to build, and you can actually use it for each of these components separately or all of them together as well. So it's not solving any of the issues of the scientific issues of coupling, but basically it's providing a really nice framework to look into all these type of things. The other idea is you want to have the ability to swap models easily, and we'll show you an example. So this is a quick recap of Skylab now is actually released on a quarterly basis. So every quarter we have a roll-up release with all our software, and it's actually publicly released, all the JEDI software. And we actually run experiments to show the software is actually running and we can analyze the data. And the idea is, because everything is under development, you want to see what are the latest capabilities. And here's an example from V1, V2, V3, and V4, where you see the different instruments being assimilated in the assimilation for the atmosphere and marine, the composition, land, and so forth. And so you see these different instrument types. Initially, we started pretty small and then added more and more. And just for the V4, here is basically the snippets from the release notes that tells you about the platform being supported, the infrastructure changes, and so you can actually go to our website and see that. So it's a nice way to plan future developments and actually release these developments in a coordinated manner. Next. So we talked about having all these different components of the Earth system under one umbrella. And if you can go next, I'll just show examples of plots that are directly cut and paste from our website. And you'll see a lot more through these demonstrations here, where you can actually have quite a wide range of observations and diagnostics that cover all these different components right now. Next. And that's it for me. I'm just going to go back and sit and listen.
So as Tom was saying, we have all of those results that are publicly available. If you want to look at them, you can go on the website skylab.jcsda.org. And when you go there, you will be able to select which version of Skylab you would like to watch results for. So all of those actually are version 4. So I thought we would have version 1 and 2 also, but I guess not. If you look at, for example, the Skylab Atmosphere Land 4.0, so it's the one that just came out a month and some ago. When you select in the observation list, you have all the instruments we're assimilating, plus a few diagnostics, for example, the analysis, the increments, some ensemble mean, because we are running an ensemble as part of the Skylab Atmosphere Land experiment, and some standard deviation of that same ensemble. For example, if you wanted to look at MCA results, you would be able to look at different channels, you would be able to look at different diagnostics, and you would be able to look at the H of X or the OBS value. The number at the bottom here gives you how many observations were assimilated from that instrument for that window, and you are able to go through the different windows. This one ran for a total of 5 days, it looks like. And so you'll be able to go through that website, look at different instruments, different results, how well the analysis is bringing, your observation closer. All of those are available on the website, skylab.jcsda.org. Now, what if I want to run an experiment like that? I would go in our code, you would have to go down there a little bit, and download the JEDI bundle repository. JEDI bundle is a combined bundle that you can use to build SOCA. Now you will be able to build MPAS. You can build EV3. We hope to bring UFS. It's kind of the master bundle that can build any model you want. And you would need to have EasyFlow installed on whatever machine you're on. It can be a laptop. It can be an HPC. Obviously, I'm not going to be able to run on my laptop an experiment such as SKYLAB v4 that runs with a very fine resolution and giant observation files. That would not work. But I would like to be able to run an experiment that is very close to that SKYLAB experiment. And so I'm going to show you how easy it is to take the parameter files that we used to run that atmosphere SKYLAB experiment and modify it so I can run it locally on my laptop that's a 4-year-old laptop. So this is a YAML file. I'm assuming most of you have seen YAML files before. It's not very long, probably about 125 lines. And I'm going to be able to modify it pretty quickly to remove capabilities that we're not interested in testing right now, to lower the resolution, etc. I will not be running for a full month. I will be running maybe for, I don't know, 3 cycles or something like that. I will keep the 3D FGAT cost function. I don't need to change that. I will probably forecast a little less long. So that would be at each analysis. I'm only going to forecast it for 6 hours. I'm going to keep the exact same list of all the observations. I might add one actually. But I will not be downloading the full observation files that we are assimilating right now. I would like a coarse sampling of it. So I'm going to be adding a parameter to just take only a coarse sampling of all those observation files. And I heard that we had a CIRES instrument we could add. So I'll just add another CIRES instrument. We had the N20, and I'm going to add the NPP also. I'll continue down the line. This here is to say that we are using variational bias correction, and we're cycling it. This whole system is cycling, will be cycling when I run it for just the 3 cycles. I have here my list of variables, which analysis variables and which background variables I am using with that system. And in the SKYLAB case, we were running an ensemble of data assimilation as well as a deterministic high-res control, member control, or control. I'm not going to be running the ensemble of data assimilation on my laptop right now because that would take too long. So I will delete the entire part that concerns the EDA, and I'm going to keep only the part that concerns the high resolution. So the EDA would start here, and I'm just going to remove all of those lines. And that's it. And I will need to, since I'm only running a high res, I don't actually need to precise that it's going to be a high res. I can just take that whole part and remove the indents that we had. Now for my geometry, I'm not going to be running with the 25 kilometer resolution. I'm going to be running with way less than that. So I'm going to change that C384 to a C24 resolution. Same for the model. I'm keeping the same background error matrix, which was a hybrid matrix in this case, hybrid being static and ensemble. I'm going to run the inner loop at a C12 resolution. So I need to precise that my B matrix is going to be at a C12 resolution. I don't need 25 members. I'll just put 3 And I will also change the resolution here to be C12. I also have access to which algorithms I want to use for this. So I already said I'm using a 3DF get cost function. I'm using an ensemble B and a static B, so a hybrid together. I might want to do my minimization in the OBS space instead of in the model space. So I could change the algorithm here and just use RPCG, for example. I'm not going to do 100 iterations per loop. I'm just going to do 10. Or I'm going to target a gradient norm reduction to be 0.05, whichever comes first. And then I'm going to, of course, make sure that the minimization, the geometry used in the minimization is still C12. I'm going to output diagnostics of O- background and O- analysis. I'm going to create some plots that are the exact plots you saw on the website. Those plots are going to be generated as I run the experiment, and we'll be populating our experiments.jcsda.org website. And of course, since I'm only running on my laptop and I'm running with a very low resolution, I don't need all those cores and all those tasks. So I'm just going to run with a layout of, 0 nodes on my laptop, but 6 tasks. And I don't need 1 hour, probably just need 10 minutes. And that's it. That's all the changes to go from running that giant experiment.
Sorry, Clementine, I know you are sharing through Zoom. Do you want to keep, can you keep an eye on the chat? There's a question in chat for you right now. Are you able to do that? Or when do you want to take questions? Right after you've run the experiment?
Maybe, yes. I just saw the question. I will answer it.
Okay, thank you.
So now just save the file and quit so I can start the experiment, which just goes with one line. I'm going to create the experiment using the file I just modified, which was skylab.atmland.yaml. This typically takes 20 seconds to generate the experiment. And it's going to populate here the tree of tasks in our workflow manager. Right now we're using EasyFlow. And to answer the question, well, Eric answered, we have a search function to know which backgrounds, which observations are available in our database. So you can see here all the tasks that are being generated. And it's going to up on the right here in a minute. Now, the question was, how do you know which observations are available in the database? And Eric answered, Eric is the person who is writing and managing our database. And we have a search method to know which one is there. So the experiment has popped up here. You can see that at the first level, we have a get ini, which is getting initial conditions. How do we start the experiment? And then we have the AN loop, which is going to be the variational loop. In this variational loop, this is the one that's going to be cycling. So I start here just the day after Valentine's Day in 2022, and then going to go for about 3 cycles. You can see them here. It's because I reduced the number of cycles I wanted to go through. When boxes become yellow, it means it has run successfully. When they are green, it means they are running currently. Sometimes when you run this on an HPC, you will see it be in dark blue. It means it's submitted and it's waiting on nodes to be available. You can see here we got all of our observation files. So all of those turned to yellow. We managed to fetch all of them thanks to the R2D2 database we're using. We managed to get our background, and we managed for each member to also get the backgrounds. This is for the ensemble B matrix. I said we only wanted 3 members, so they are all 3 back. Yes, because I said I wanted some course. And on my laptop, I don't want to do the coursing after the fact. Very fast, yeah. And in that case, when we run on laptops, we're going to make sure that whatever actually makes it to your laptop is a low resolution. We do want to eventually make that an option on the fly. We'll see how we can. So the variational task is usually taking about 2 minutes because we have a lot of different observations to assimilate, even if those OBS files are pretty low resolution. And then you can also see that I'm going to be creating some diagnostics. I have variational diagnostics that are log-based. It's going to be cost function. It's going to be, mainly cost function and impact of observation. I have analysis here that is going to be plotted and published. So any task that is named published will mean it's going to get populated on the website. And of course, I have my forecast task that I need so I can go to my next cycle and have some background to start from. And in the feedback here, if you go down, you will see that it's saving all the feedback for the observations, and it's creating plots also and publishing those plots on the website. Now, for the sake of time, I'm not going to make you watch all those boxes turn yellow one after the other, and we can just go and start looking at the results. I have run this experiment already beforehand, and I can show you the results. And we'll also be able to see then as the plots get published and arrive, but they arrive one by one, and we're not going to refresh the page every 30 seconds. Yes. And so the way it works, I cannot see. I can't access the top level. So this is the experimental version of the website we just looked at earlier. This one gets populated with all the experiments that we have been running on HPC, on my laptop, or anywhere. So I need to select my name here. And then I can select an experiment. For example, I just ran something that I have previously ran before, atmosphere small. And I can look at some diagnostics that were log-based. So for example, this one, which is the fractional impact of each observation. Of course, I'm not assimilating a lot of observations right now, so those plots are not very scientifically relevant, but they are a good first step to know if my observer is working correctly. I don't have a crash in the system somewhere. I can also look at all the instruments I've assimilated. We could look at, for example, SOA. You can see here the coursing, which is way lower than what you have looked at before. Just added, I don't know, that CIRES instrument. This one has 6 observations, but that's a very, very coarse sampling. We could look at GNSS-RO. We have a lot more observations. We are trying to keep a somewhat relevant ratio of how many observations we keep compared to how low of a resolution we're trying to run, so that we don't flood a low resolution background with 1 billion observations. You could look at aircraft. If we had aircraft, oh yeah, they are here. So you could see them over the US, and you can see that, we have the O-B that we were looking at before. Here, -999 is just because we're only running the control. But if we were running an EDA, you would have a choice here of, you could look at individual members. And I have run that for 3 cycles previously, so you can also go through the different cycles and look at the results. And the other experiment should probably be going steady now. I need to click my name. And this is the experiment I just started, and so you can see that the plots are starting to arrive, but we only have access to 1 cycle for now because it's not run all the way through just yet. This one, for example, JOJB would be a time series. If you are cycling your system throughout the entire month, you could look at, every cycle, what was your initial JO, what was your final JO. For example, I know that this one has run for a full month. And so if I look at the last cycle, or in the end, you're going to really see the impact of, when radio sounds are, and then when you don't have any at 6 p.m. and 6 a.m. So you get this movement throughout the day, and you can. So we're trying to have as many, informative diagnostics as possible, with keeping in mind that we don't want to populate 1 billion plots every time we run something. we have some diagnostics that are log-based and some diagnostics that are actual feedback-based. But all the ones that are under the var diags key are log-based. And that's it for the... Okay. Does anybody have any questions?
I was just going to remind people to use a microphone so that everyone in the room can hear the question and people online.
Getting up too often.
What's that?
Okay, so I'm going to continue the demo and then showing an example of our aerosol experiment that I talked about in my talk. Again, this is going to be a smaller experiment with lower resolution, and I'm going to show you like what we need to change in the YAML in order to change the model and also some other setting in the experiment. Okay, so I'm not going to edit anything here. I'm just going to point out the main changes that we can see if we want to run a GFS aerosol experiment. So to start here, in the suite, we have cycling EDA for us. The model, we changed that from GFS to GFS aerosol. So that's the model that we are using. So here you can see that we are referring to all the tasks that are different between GFS and GFS aerosol. So there are like small tasks that are different and we needed to code them a bit differently. So we have this here to use that. So we are running 3 cycles here, I think. And then as we go further, so the cost function is different for us. We are running 3D bar experiment in this case. And then the window mode is just 3D bar. So we are running non-cycling, meaning that I also mentioned that in our talk that we are not going to run model. We are not going to start the next cycle from the new feedback files. We're going to start it from background files. So that's different. Another difference in our case. And then, so Clementine talked about upsampling course, and then we have 4 observations, and you saw the results in my presentation from these instruments. So obviously the variables are going to be different for us. We have aerosol variables in our simulation, and we want to assimilate those. So we have that. These are different kind of keys or YAMLs that we need to use in our experiment. And also we will have 2 members and running with C12 and C12 resolution and 64 vertical levels. For the model, we are running identity model. So basically we are not doing anything. So the kind of feedback is going to be the same as our analysis. And then, so for background error, there are different options that we commented out this part. So this is just a simple identity static B that is very useful for testing if you are kind of trying to add a new task or new feature and you don't want to spend like way too long on the variational step. You can just use this YAML. It's pretty simple and very useful. But for this case, we are using a static B for the variation step. Again, Clementine talked about these, so I'm not gonna point these out. And again, for plotting, we are plotting different variables, so this also changes. I think I covered everything. Okay. So I'm not gonna run this experiment because it's gonna. Oh, okay. So I'm gonna. I'm gonna again, same as the experiment that Clementine ran. I'm gonna use create experiment.py, and then kind of use my YAML experiment YAML to run this experiment. That was quick. So if we go to our EC flow, you can see that the experiment is here. The experiment ID is this number, and we can use that when we go to the website to look at the results. Similar to the previous. Do you have a question?
So create itself just also launches it?
Yeah.
Okay. Okay.
Yeah, so it will create the experiment and start running it basically.
You guys are smart. I have a silly question. I don't really remember these things. I can remember yes or no, or can see the list, the schemes, the models. So how do I, do the configuration set up correctly? So I don't want to try one by one. So all these schemes, you have limits, right? You have a list. My question is, how do I set up? And, as a new users.
So when you're a new user and you're already familiar with maybe running at least C-tests in the JEDI bundle, then you have a few extra steps where you need to make sure you can connect to our database. You need to make sure you have downloaded the appropriate repository, for example, the SKYLAB repository. And you will find already a list of schemes that exist that you can play with. And that is typically how we try. For example, when we added the Aero GFS model, we started from a GFS standard composition, and they didn't have a B matrix at the time, so we were using an identity. And you can build off something that is already existing and modify it and play around until you have all the blocks ready for your own model or your new observation or your new system.
Yeah, my question, if I was a graduate student, I was a graduate student, I pick up this, I said, open the YAML file. So how do I, is a list, is JEDI-based, it's GEOS, it's all these things there, just open the YAML file. Can I see that, or can I go to some website to know? As a new graduate student, I have no idea about all these things. Okay,
we have a lot of example YAMLs that are very useful. Yeah, there's that, and also the documentation. You can refer to that. But I would recommend looking at the YAMLs that are already there, because there are a lot, and there are a lot of good examples there. But documentation is a good place to.
You guys have a few questions in the chat as well. If you can keep an eye on that, thanks.
Yeah, so I ran with 2 members because I'm running on a laptop that doesn't have the power to run more than, really 1 member already. So I'm not trying to fry it right now. So why 2 members? It's just limitations of my laptop. And can we change experiment ID if we would like? In my case, I forced it to be something readable when I was showing you the atmosphere small or aero small experiments. And Eric answered, yes, you can rename an experiment, because all of our experiments are stored in the database that I was talking about. And you can move from those 6 random characters to another 6 less random characters or 4 characters or what you want. Ah. Yeah, the other one was
Okay, so any other question while we are waiting?
I have 2 questions. Well, can we see how you specify as a graph for the experiment? Because I think a lot of us will be interested in actually modifying the graph of how things are plumbed together. And a second question, we would like to run it with known prototypes for the model. Like, what would it take for you to run UFS HR1, for example?
So we actually have 1 or 2 experiments running with UFS. So it's obviously a little bit more complicated than other models, but it's very, very few examples. And Clémentine has a talk tomorrow where she will talk about running with UFS. So if you can wait until tomorrow, you will see that. And for the graph, yeah, it's well, I can show it in a minute once Mariam is done if you want, but it's not a graph, it's a Python code. It's all Python based. I'll explain that.
Okay, so what about if you want to change to a GitHub feature branch of UFO and combine it with a feature branch from EWOC area and get both of those 2 things together in a Skylab experiment? How do you achieve that?
So you do have to start with the first step, that is building the bundle, so the JEDI bundle. And if in the CMake list of your JEDI bundle, you specify that you wanted a different branch for UFO, then it will use that branch in UFO. And it's the same for all the Python-based code that is not being built. If you check out a feature that is different, it's going to use that feature.
Can you say also a little bit about R2D2? How the database is organized, input dataset, output dataset? I believe this is connected to R2D2 database, right? Will you say something about that or maybe later?
So I know that Eric was listening in and he is really the R2D2.
Yes, I'm here to answer. Can you repeat the question, please?
Yes, you. I'm just saying, okay, will you tell us a bit about how R2D2 works? That's pretty helpful for student also.
Yeah, so we'll talk a little bit about R2D2 tomorrow, but basically R2D2 is a front-end Python API, which integrates with the MySQL server. The server indexes all of the metadata and data files, and then it also, in the Python integrate, the Python API then accesses the MySQL server, and it will go and find and fetch the data files that you request, depending on where your location is and where the data store is located.
And I think, Eric, you have a talk tomorrow, right? About R2D2.
Yes. We're going to be talking about R2D2, YODA, and how those apply to FAIR principles.
Okay, so if there's no more question, it looks like okay, so it looks like we made some progress here. So you can see the 2 members, background tasks, analysis task. Member 1 is done, member 0 is still running. Well, it's done. And now we can take a look at the results on the website. So here's the result. So the fractional impact. So we only see VIRS MPP because the other three are in monitoring mode in this case. So similar to what Clementine shows, we have different types of plots. We have analysis, we have increment, and we have the variables that we specified in the YAML got plotted here. So we have dust at different layers in right locations, which is good. And then sea salt. And then you can also pick different observations or instruments and look at O minus B, O minus A plots and compare the improvements. Yeah, and also we only ran for one cycle was done. So you can see that here. I think that's it for me. Want to stop this?
All right, so I'm going to continue here a little bit. First, I'm going to suspend that because of, oh, okay. Because I know Clementine wants a new laptop and she would love for me to fry this one, but I will try to keep it alive until the end of this demo. Obviously, we've shown you some GFS-based examples so far with the aerosol and what Clementine has done with GFS, but I'm going to go back to what Clementine was doing, and which was the SKYLAB atmosphere and small, not small, no, sorry, you're running the real thing. Okay, and you know, obviously, like everything we do at JCSDA, when we start, everybody tells us it's absolutely impossible to do, but this workflow can handle a whole bunch of models. So I'm going to show you I run with a different model here, and I'm going to run with MPAS for this example. So I'm just going, one thing is going to change to a static B because I don't have the ensemble here for on this laptop for MPAS. So that's good. And then I'm going to just go and look for GFS and replace it with MPAS. Not this one. I'm going to use the bias correction coming from GFS. I don't have one for MPAS. So just changing GFS in MPAS basically, and we have different YAML file that define you know what the variables are for MPAS, and the resolution also is not specified the same way, so it's not a C24 or C12, but it's given in kilometers. So I'm just going to replace that here with a 480 kilometers, the one we have here, and I'm going to do inner and outer loop at the same resolution. So there we are. And then the other thing I'm going to change, so this MPI layout is not needed for MPAS, and also I'm just going to use one task here. And oh yes, one other thing, so MPAS is a little bit simpler, so the background variables actually here the same as model variables. So all this will be documented. Obviously, I've done it, but to answer the other questions that we had earlier, and we will put the idea is that we don't have resources to do it immediately, but there will be a GUI on top of that. So instead of VI, you will have actually slightly more advanced GUI in the future, but will give you menus of what you can choose, and you can also add your own YAML file if you want. Like as you see here, is a path to a YAML file. If I wanted to change, let's say the background error matrix I'm using, and if you know how to use BUMP and how to generate a YAML file for BUMP, but a few of you know how to do now. You would just put in your YAML file there, and then the system will assemble, put it where it needs to go in the overall YAML file for a variational DA, and use that. And what else am I going to change? Yeah, I'm just going to change. So RPCG actually works with the class. I've tried it, but I'm just going to go back to the upper Rosati preconditions. Shows if I can spell it right. Yeah, and that's all. And so I'm just going to go back to the bit experiment here. So maybe I didn't make too many mistakes. Then it will work and run. Now, the nice thing, as you see, I didn't change anything related to the observations. I've kept the 3D FGAT cost function. I've kept, I've fiddled here with the minimizer a little bit, just, you know, to go back to the more classic Derby Rosati minimizer rather than the RPCG. But if we look at the results, once this has run, we'll have one run with GFS, one with MPAS, and we can really compare apple to apple because it's the same YAML file for the observations with the same QC filters, the same observer, the same everything. So I think that's going to be a really nice tool to do some interesting science there, where we can, you know, we can start experimenting, compare. Hopefully, we'll have GEOS in there soon. The main, yeah.
So what stands between? Is it just SPAC? That's it. Once we to get GEOS in there, it's just SPAC.
It's basically that. Yes.
Okay.
Yeah.
Noted.
And yes. Okay, good. So yes, as soon as we have a version of GEOS that we can compile here, we'll add it to that system, and you'll also have GEOS as an option that you can run. So yeah, it's going to take between 1 and 2 minutes. I think the variation, goes a little bit faster with MPAS, but still it takes about a minute, I think, to run on a laptop like this. Now, yeah.
No, I was just going to ask along the lines of what you were just saying, of having the ability. Now you have all these experiments that are sort of similar, but not quite identical. Mm-hmm. Do you already have the framework to compare them, or you're building that framework?
We're working on it. It's not there yet, but we're working on it. Yeah, so just to show you that it's not just GFS and MPAS. Here I'm going to start one. I also have a Lorentz 95 model for the VAR cycling that should run faster, and that I'm trying to help her get a new laptop. That's yes. So sorry, yeah. So here it is. It's going, with Lorentz model. Obviously, it's a lot faster. So things are here. You're going to start seeing you should start seeing the cycling very quickly. But the nice thing here, and I can show you the YAML file again for the Lorentz model, which I just started. And you will see it's very, very similar to what you've seen with GFS and MPAS. It still has difference here of cost function and for DVAR. But other than that, you have all the similar things. There's less observation, background error is simpler, but really it's the idea there is that when somebody is new to data assimilation, they start with this tool, they run a Lorentz model, but at the same time, without even knowing it, they are already learning and building their knowledge so that later on they can run a full-blown operational system, all within the same framework, the same tools. And that's really the goal here of this entire system. Just like OOPS and JEDI itself is generic, the workflow here is generic as well. And it's built on the same design ideas as the data assimilation itself. I start hearing the fan on the laptop going here. So since somebody wanted to see the how the tasks are specified, yeah.
So this is about JEDI-EDU. Seems that Skylab should be okay. You understand what I was going.
Yes. So definitely. So what I'm showing here with so there's the lines 95, there's the QG. So we are going to start building all this JEDI-EDU on top of this tools, and really have something where students can interact, see the plots, and change something in their observation, run it again, see the plot. That's really the idea. So just to give you an idea of how the suite is generated, I'm just going to take I'm not going to show the entire file here, but the one I wanted is here. So for example, here I'm having it's a Python code basically that's generating this suite of tasks. So here, for example, I have a variational task with its configuration is taking a bunch of arguments here. And it's producing an analysis. That's the key. That's what you expect as an output from your assimilation. And then this AN, you see that here you have a forecast task, and the initial condition is, so there's still this line here, which is not very nice, but hopefully we'll get rid of it at some point. And this forecast, so it's basically the initial condition is basically the analysis here. Sorry, but there's still a bit of syntax that needs to be cleaned up. But here we're passing the initial condition as an argument to the forecast task. And just from the fact that it says that the output of this one here is used as an input here, it's going to put the trigger here and know that I'm going to mess up your nice arrangement here. And we see here that the forecast won't start until the variational is complete. And so it's only based on what's an output of a task is used as an input for another one. And that's why, for example, we have executable here is an input argument for this forecast. And if you look up at the top, there is a task called build JEDI. So until the build task is done, the executable won't be available. So the task that needs the executable won't start. So it's the entire system is built on that. Just a loop. Yeah, I can show you.
How would you specify that these tasks can all run in parallel versus there is that kind of thing?
It's just a loop. Like for example, here, we have a list of observation, and we have a loop, and because there's no, so it's the getting of fetching of observations. But because there is no output of one that's used as an input to the other, it knows they can all go in parallel and there's no dependency. That's all.
So does it evoke that does all the parsing and say?
Yes.
So okay.
Yeah. So the only thing, if you want to make a change and add a task, you edit that one file and then create experiment, and the whole mechanics is hidden underneath. All right. Yes. And the laptop is not dead yet. Okay. Okay. Yeah, so you see the L95 has cycled already, several cycles. And the MPAS is here. Here's your browser. Okay, so that's the experiment that we just started that's running with MPAS, and as you can see, it's producing some fractional impact. I mean, given the resolution here, it's not always looking super good for some of the ops types. But at least you can see that it's running, and you can start debugging your stuff and testing and then you can run some higher resolution. So I'm not going to go through all these plots because we have the same. So I'll just go back to and yeah, go ahead.
So so I think this is all very strongly dependent on R2D2, right? So
yes.
So the initial conditions, everything goes into R2D2?
Yes. Yeah, so all the observations files are in R2D2, and we have a command to fetch them when we need them. In the backgrounds as well. So here, because I'm cycling, it's actually only the first background that's needed from R2D2. And then when you run your cycling, it's actually using R2D2 locally to store an analysis and using it to start the forecast. But because it's cycling, it's all kind of self-contained, except for the first one when you start. Same thing for the bias correction coefficients. They're in R2D2. You fetch them, and then if you're cycling, then it's just kind of keep using it. You need the first one.
Yeah, Nick, can I make a quick comment here? So there was one misconception that came up in a previous conversation with other people, and just to clarify this for everyone, R2D2 uses a MySQL or MySQL server for storing metadata. The data is stored physically on disk as whatever netcdf or something files.
Yes.
The metadata only knows where to go and find the files. There was one of the concerns that the operational centers brought up is what happens if we hide all this data in MySQL thing. It's very difficult. So the data is physically on disk as a file, and the metadata knows. Metadata tells R2D2 where to go and get it.
Yeah, it's a good point. It's only the metadata that tells you where to find the file, and the file can be locally in your machine or it can be on the cloud, and R2D2 will know where to get it from. That's the idea. Where did you put the slides? Yeah, go ahead. Okay, good.
I'm just going to look at the chat because we have lots of comments.
In case you have questions, yeah.
It seems like Eric has answered all of them.
No, good.
Thank you, Eric.
The laptop is dying.
Are you reading questions right now from the chat? Okay. No. So for an to run this on any HPC, and you really want to run a big experiment, it's just a matter of having EC flow.
Yes.
That's it?
Yeah. So if you, well, good.
It's a matter of having spec stack.
Well, we already covered that.
Yeah.
EC flow for the workflow, not for the model.
Yeah. EC flow is in spec stack.
Ah. I see.
Yeah. Can you put the slides? Because some of these things are covered in the slides. So, yeah.
So what if I wanted to use Skylab just to run a simple HFX on backgrounds that I already have somewhere and observations that we have somewhere else? Would I have to ask one of you to put that into R2D2?
Yeah, well, not really. You can do it yourself. So if you have a local R2D2, you can. So this, I'll let me go through this thing, and I'll explain, and then Eric can explain even a bit more tomorrow. But yes.
One last question.
Yeah.
Let's say I didn't see how you were setting up your background area. Is it assuming that everything is the same for each models?
No.
Or, okay. So that's a task that's set up in the model interface itself.
Yeah, so it's basically it's a snippet of YAML that's the config you would use for BUMP or your identity background error covariance that you use, which in which case it's a fairly simple one. So it's the section of YAML that goes, in your when you run a JEDI assimilation, you have a portion of YAML that describes the background error. So you just put that in a file and you point to that file, and you can just go and replace that file by a new one if you have a new background error. Yeah, go ahead.
So with ECFlow, I mean that pops up. That's like a browser-based GUI, right?
It's not a browser. It's an application. Yeah, it's not browser-based.
So I know we had chosen one of the reasons Silk was that we couldn't do that on Discover. Well, What's our recourse? Let's run it a different way, like a TUI instead of a GUI.
Yeah, no. So, well, it's on my next slide, but yeah. So basically, this thing is abstracting away the workflow, the actual workflow engine or whatever you want to call it. So EasyFlow, and we have in the plan for this year to add the support for Silk. So you can choose if you want to run your experiment through EasyFlow or through Silk. And I
didn't want to ask you that question directly because I thought we disincentivized you about doing Silk because we were doing it. Well, then why do we have to do it? But okay.
Yeah, I mean, we'll try to do it this year to have Silk support. I think, so we started with EasyFlow because it had at the time when we started this work, it had the Python interface, but Silk didn't have. Silk now has it. Yeah. So it's easier to integrate with this system, which is fully Python based. So we will work on Silk support at some point. If some in-kinds want to help, yeah, more than welcome. Okay, so, well, we've gone for more than an hour, so I'll just go for some conclusion here. So now, as you've seen, this eWork plus R2D2 environment, something we can run toy model low-res, full-res systems on laptops. It works in the cloud. We've run it on AWS, and we'll test it on different cloud platforms and HPCs. We have a number of HPCs that we've tested this on. So mostly Orion S4. Cheyenne, a bunch of others, but we can add some more. It supports in principle everything that you can do in JEDI for changing your YAMLs is supported here because it's just basically templated YAMLs that generate the YAML that you would So until now, most of you were looking at these very long YAMLs and editing them by hand to run JEDI. So now it's snippets. You have one YAML file for your B matrix, one for ops type, one for minimizer. So you just go edit these very small YAMLs, and the system will assemble them and generate this giant YAML that's driving the application. So it's a lot easier to work with that way. And we have created data sets in R2D2. So I think that goes back to the question from Guillaume. So R2D2 will contain some data that we curate that we will look after, and it will have some special labels that, okay, that's the kind of official supported set of data. But then, it's a database. You have a store command and a fetch command. Nothing prevents you from storing files in there. I mean, we've done it for testing. You have your files that you want to use. You have a store command. It will push all these files into R2D2, and then your experiment will run and will fetch them. And as long as you have the correct observation type and date and thing, it will just fetch these files. And so you just use the store command to put data in there. That's
have about 1 petabyte of data. Can I push it to R2D2?
If you have a storage, yeah.
But I guess the serious part of this question, do you see a federated approach where, say, NOAA provides a backend storage for, S3 for their data sets, and there is a way to connect your MySQL metadata to the data that we store in whatever way,
So without going through the store command, pretty much no. I don't know how that would be doable. That would be a lot of work and would not be, it's not designed for that. Really, in order for the system to know where the data is, you have to go for that store because that's what's going to create all the index. Eric will talk about that more, but that's what's generating all these indices that that you need to go and find your data later on. And if you don't generate this index,
can't you make a register command?
Well, let's not go into this technical discussion now. That's not the place for that. I think that's, very good. So, yeah, well, we have the backgrounds, we have files that are in YODA format. So we have a number of supported formats that we, the idea is that also it's possible with some files, not with others, depending on the format, that R2D2 will check that you're not lying to it when you're putting things in. So if you put the date, it's not the date that's in the file, it will tell you, you're lying here, but that's not implemented at the moment, but it would be nice to have that extra feature. But that depends really on the file format. And so, yeah, sometimes it's nice. Yeah, sometimes it's nice. But, you in an operational system, you don't want accidents like that to happen. So you want to put a layer of checking things. So we'll try to build. That's why it's difficult to support things that are, that all over. We need a bit of structure in order to build this index and know what is where. And also the important part is there's consistency. If you're running on Clementine's laptop or on AWS or on Orion, if you fetch a file, the system will check and you're getting the same file. So it has a consistency checks across different platforms. So there is a bit of if we want to be able to be to reproduce experiments, we have to ensure that consistency and ensure that we have these levels of checks. That's why it's difficult to just put anything in there. You could put all your pictures in there, but that's yeah. But it will evolve a lot. Obviously, GMA was fully involved in this R2D2 development, and potentially it could grow a lot and become a service that becomes available for the science community, that everybody could just go and fetch and say, okay, that observation type for that date and fetch and do whatever they want with it. Obviously, somebody needs to fund that. The storage is not for free. So we'll have to see. Yeah. Okay. So next steps before we stop. So at the moment, as you've seen, is very flexible. You can run with many different models. What we need to add here is the support for multiple models in the same experiment. And then so that we can go toward, I say multiple coupled. I don't like this idea of weakly coupled, strongly coupled. It's all, you could imagine a very, very weakly coupled where you just have two models running side by side without being coupled, all the way to a fully coupled everything. And so we need to add the support for that. It's probably not a lot of work that needs to be done. Tutorials, they are, we have some documentation, but it's not completely all there yet. So we're going to develop some tutorials, and we're going to really use that environment for teaching this environment and for teaching DA. I think that's a very nice tool. What we want to work on, I touched on that a little bit, is management of experiments. So that means several things. That means storing all the information so you can actually reproduce an experiment and be confident that it's really reproducing the experiment you originally ran. That's why we need to track the data. Eric will talk about that tomorrow. Track which version of the code, the tags of the code, the actual commit that were used for that experiment, and etc. So you can later on come and say, copy that experiment, rerun it, and be confident it's really reproducing your experiment.
From what you were showing, and then somebody edited this, what's missing from that process now?
So it's like, for example, the experiment we just ran here on Clementine's laptop. If I came back tomorrow, we didn't store the commits, like the version of the code, which branch of the code. We were running on develop for the code, but we didn't store that. So we need to be able to store that and fetch it, get it back later on.
Along the lines of this storage stuff for reproducibility, isn't it, when you're talking about models like MPAS, GEOS, and heaven knows what, the complexity of that is much larger, right? Because GEOS, for example, has a zillion of boundary condition emission files, and that's even worse. So how do you plan to sort of keep track of that?
Yeah, there will be some work to do there in order to, but so I think Dom will tell you SPAC stack is a nice step towards that because you have all your base library, you know what they are, you have the hash of a SPAC stack, so you know exactly all the underlying libraries, and then you build, you know, but yes, there is a lot of information to record. And if all the data is in R2D2, then in principle, you know where you got it from and you can fetch it again. And but I agree, it's complicated.
Yes. You have, if you have the hashtag, you get the source code guarantee, but you don't get the supporting fields that actually allow you to run it. So it could be that somebody changes that. And then, you know, so.
Yeah, so, you know, the backgrounds are in R2D2. We plan to put a lot of the what's called fixed files, you know, that also in R2D2, so they get fetched from there. So then you can have version there and you can tell the database on that version. But yeah, it's going to come gradually. We're not going to do that in one day. Yes, and as I said earlier, also the GUI, that's a little bit nicer than VI to go and edit these things. It's actually, Tom has a lot of ideas how to do that, so we'll let him do it. Yeah, more on improved diagnostics, as you know, the big thing that's really missing is that we run these two experiments, but we don't have a tool to really do a plot of a difference, and that's something we really need to be able to do. And we discussed, support for silk already, so that's also something we want to work on. To the last slide. Okay, so last slide. Well, I think we've covered most of the points here, and Tom kind of already mentioned them in the introduction, but just to reiterate, the idea is, you know, we would start, and we've started a little bit with, you know, CSU in particular to develop some this JEDI EDU for training students, where we would start from a Lawrence model, QG, you know, shallow water, go all the way, and you know, the idea is that they would use the same environment. So when they come and they get a job at GMAO, lucky ones, from day one, they know how to run that system. But it's yes, and we're also putting in place. So we have, you know, these high resolution runs for SKYLAB. We'll have what we call a medium resolution and a small that you just store on the laptop. So that's this kind of idea of hierarchical testing. You can do a quick test on your, you know, on the C12 or something to see, okay, and then you move to a whatever C96, and then you can move to C384 or whatever resolution you want. That's all in the same system. You just change a few lines. One thing a few of the partners of the JCSDA said they're interested in is this O2R, so it's proxy apps. So we would like, with all of you, to build applications that we can put in that environment that mimic what you're using in your different labs or you know, so that we can actually, that's the number of, we can actually test something that's relevant for you. You know, students can learn something that's relevant for you, etc. So we would like to build these proxy apps. The goal there is not going to, you know, Guillaume was talking about this last mile. We don't necessarily want to do the last mile in these proxy apps of all the downstream, you know, product generation that an operational system might have and things like that. But hopefully something that's close enough that is relevant for you.
Like a reasonable set of observation YAMLs or something like that. That's kind of representative of our configuration. Yep. That kind of thing.
Yes, and you know, if you're running a 4D envar, we'll put a 4D envar in there, and this kind of that it's kind of ballpark what you're running, so that it's close enough. Yeah. Yes, when we apply to GMAO, we'll be able to show you the experiments we've run, and you can look at them. And finally, the thing that so we are doing in the core team, and we are hoping the in-kinds are going to start doing soon, is this, is the what we call R2O, at least the first step of it, that people have a branch, they would run an experiment with that branch, they can look at the result, If it's good, they do a PR, it gets merged, it gets in the next quarterly release of JEDI-SKYLAB, and then it's available for all the partners. So people in the team are already starting to do that, and we are really hoping that more and more people in all the in-kinds can also start using that soon. And anything more to conclude?
That's it. So basically, just to the take-home message, we're planning on releasing that service sometime in the summer. There's still some work to do to document and package it. Just the take-home message is really focusing on ease of use, and at the same time making it flexible to actually allow for sandbox experiments, really for scientific experiments to be blossoming.
Well, the question to you then is, when is the next academy? Because it almost sounds like you could have another academy.
So we're actually planning on using this environment for the next academy. So there's a little bit of a chicken and egg thing. We're trying to actually make sure we have the timing right so that we do this. So I think we'll get there soon in scheduling that.
And we didn't kill the laptop, but Clementine will get a new one soon.
There's a bit of time left for the posters, for those additional posters today. So please have a look, and we'll adjourn around 5 o'clock. It's been a really great day. I enjoyed it. I learned a lot. Thanks everyone for all the sessions, and enjoy the posters.